darfst du noch nicht stoppen.
Nein, ich muss nicht, aber guten Morgen sagen.
Ist der nicht? Okay, hello, good morning, welcome back to next session. I think the title is What's New in NGSolve? I got planned what's new in NGSolve, but that's a good question. Yeah, the last days some of the young guys are asking, okay, I'm very excited to learn what's new in NGSolve. When we have learned the last year, all what we have done the last 20 years in NGSolve, and I'm very impressed with seeing all of this material. And expect coming back after 1 year to see as much as new stuff in NGSolve. But well, not that much as we have done previously is now also new stuff. And okay, now I will show something what is really made possible over the last year. And I want to say also about some. I often get question: can you do this in NGSolve? Can you do that in NGSolve? And why can't you do it? And well, you know me, I'm quite critical with methods, so the claim is that all good methods you want to have in NGSolve, and it could mean that methods, I'm convinced that they're good, and you have to convince me that they're good and they scale and you can solve them, then that sometimes they will get into NGSolve. So it's good methods, bad methods, mathematically interesting methods. So people ask, are there C1 methods in C1 continuous method in NGSolve? IGA or some queries or okay, there are 2D, 3D. Okay, there are C1 methods in 3D that the header matches. Yes, it's possible with I think 8, 9 order, but I think they're not very interesting, but the motivation to get them into NGSolve is good. Some methods I thought are, well, I have a little bit thinking that they are not good methods, like boundary element methods, and I think now they don't get into NGSolve, but sometimes I change my mind, I get convinced by someone that it makes sense to bring them also in. What are good methods? I think when you have hard problems and easy problems. So what are hard problems? For example, if you have anisotropic second order equation, it's very high undirected anisotropies and it's a hard problem, and anyone please tell me what to do there except putting high order elements on it, but few ideas on how to solve this robustly. Helmholtz equation I think is a hard problem. There are some doing it with standard methods. Well, there are some approaches for solving them, but really good different. There are some double constant multiplier methods which are good for Helmholtz. So it's Helmholtz is on the board. Is it very hard or doable? But there are some methods for simple problems which are too difficult. And I'm not so much a fan of solving simple problems with difficult methods. So, example, if you do Poisson equation and you see two continuous elements. You can do, yes, you can do it, but I'm not convinced of it, and this high smoothness for second order. There are more of this. Or doing Maxwell equation with vector H1. Certainly you can do it and people are fighting for it, and yeah, you can use the Lagrangian elements for Maxwell. Sometimes it works, but you fix one problem and you run to the next one. So you have natural elements, doing the dynamic elements, and everything is smooth. So there was a fight in the 90s from going to vector H1 to dynamic elements, and now I think everyone is convinced to doing the right method. For Stokes, well, so we are convinced there is one right method, isn't it? Well, for Stokes it's very ugly. There are a lot of methods and no clear favorite. in the general community as it is. I hope I'm not speaking on. Okay, to engage with conforming is a right method. B. Always right thing to do, and everything becomes easy and nice with this. I will show today. For shells also, if you do this very old Hermann Johnson, it looks complicated in the beginning, but then you can do the mix method, it looks complicated in the beginning, but then you have simple possibility. You have seen in the talk yesterday in the bachelor thesis, you can do the shell and you can put it in a coupled field simulation, and it's easy to use for a more complex environment. So you can go from the model unit square into a 3D and couple it with some fancy shells. Okay, and let me give you a short definition of what I mean with good problems. Good problems are which you can solve also efficiently and scalable. Where you don't need a direct solver, you can run the iterative solver with a good preconditioner. Good methods are also friendly to the solver. Friendly to the solver in general, friendly to the solvers available inside NGSolve or from external packages. And now with section 216 and 217, we have added some missing features in NGSolve, so to say. How to do multigrid also for high order spaces. That was implemented around the user meeting last year. Okay, let me show what we can do now, freshly with this. It's linked in this Google Docs document as pointer to 216 and 217. You may use the iTutorial documentation with the test version to see it. Tutorials. Default I have it maybe in the browser cache. If you go to test here, you find the 216 and 7. And maybe you try the examples also on your computer and you do it hands-on. Okay, what is new here? Okay, I have here a coarse mesh and I have a high order file element function, let's say order 10. We have something high order. I put some function here on it, and you see you need a high order to resolve a couple of waves on one element. If we do now mesh refinement, we want to have the same function updated on the final grids. There was a flag, if you refine, you update the final element space, you update the grid function. This is now going automatically. If you refine the mesh, base getting updated, grid function getting updated, and we see the same function on the final grids. Okay, what you see is we have this funny kind of mesh refinement. It's done by bisection. Bisection means we cut every triangle into two triangles, again and again, with a pattern such as it's this triangle stays bounded. While bisection, you can do it adaptively to do local refinement with this. And it's also easy, you have just one triangle split into two triangles. You have to worry how you prolongate the function from one to this left and to the right triangle. If you do red-green, you have much more cases. Okay, I was quite a long time afraid of implementing this, but now it works for most of the spaces. So what do we do is I've implemented it for L2 spaces, just polynomial the big one, polynomial to the left and polynomial to the right. So L2, so we have these vertex-oriented basis functions. There's a few classes. You have to take care also of the vertex orientation of the chords and the final. we have a certain number of classes, so 2D, I think it's 32, 3D, there are 500 classes or so. So we store the prolongation operators only for a class of reference elements, for the class of reference elements. That allows you to do it for L2 high order polynomials. And now we want to do also H-curl, H-diff high order prolongation. So for H-curl you have to prolongate on edges and faces, and the fine grade edge depends on the coarse grade face and so on. Well, there's less of this, but the simple solution is to transfer the H-curl fem to an L2 fem, use the prolongation in L2, and go back to H-curl on the fine grade. For this, you have to take care of the map. And this prolongation, these are prolongation matrices, but only for the reference elements. Not for all individual elements in the mesh, which would be a lot of memory. You want to do it on the reference element. For this, you can transfer from H-curl to covariate mapped vector L2, which works the same as L2, and it's difficult to back to Pirola mapped vector L2. So essentially, we can take now this high order prolongation for all of the usual function spaces, which are out of the Theron sequence. You don't get it per default. You have to enable it by setting high order prolongation flag in the final element space. There are some restrictions. It works only on simplicial elements, so for some reason we may have, for thin layers, we may have mixed meshes with prismatic and pyramidal elements. It may crash there. It works for fun by bisection, and it does not support by now variable polynomial degree. So we can have different polynomial orders in different regions, but this high order prolongation assumes one fixed order. Okay. If we don't do it, let's also see what if we don't do it. Okay, you get also something. What to do is it just takes the low order degrees of freedoms, lowest order space, and does a low order prolongation. This was the way to go. Okay, it's also doing something useful if we start with a finer mesh. Oops. Finer mesh on. Okay, this is only doing the lowest order components. You see it's also doing something, but not, certainly not accurate. Okay, you needed to want to solve a coarse grade and do additivity and have initial case on the finer grades and you prolongate the solution. And you need it also if you want to do high order multi-grade methods. So we have the geometric multi-grade. So you have a hierarchy of meshes, spaces, and you have it's a grid transfer between the spaces. And now we can do map the high order fine elements from the coarse to the fine. Okay, so we run the problem, order 5, high order prolongation activated. As a precondition, we do a multi-grid, do a couple of mesh refinements, checking for eigenvalues. Oh! So this is just some smoothing iteration per level, vertex patches. I was running multi-grid for a while, but I never got such good condition numbers. So before we only did a low order prolongation, which is okay for the high order spaces, but having coarse grade corrections, also high order gives quite good condition numbers, and also iteration numbers if we solve a problem. Well, 7 iterations, 10 to the minus 13. And also not slow. So we had 200k unknowns. I can also do a bit more here. Maybe 6. Okay. Well, 700.
It was good you solved the whole stuff.
Right? The course grid we said that solver, yeah. So we also with high order. One could choose a different coarse grade solve, also going back to the lower or AMG or whatever. And did too much. Yeah, a couple of millions should. Yeah, 3 millions now. And also if you iterate the okay, it's okay. You do a smoother, to have blocker side, to have a reducer. Question what are the blocks? You do solve a small system on the edges and degree of freedom on the faces, or to be more generous and solve for the vertex patch. Now we can. Okay, so this. What are the vertex patch? Vertex patch means you have the elements connected to one vertex and all degree of freedom internal in this vertex patch, not including the boundary of the vertex patch, and all degree of freedom sitting in this vertex patch are combined to the blocks in the blocker side iteration. You can define your blocks from Python, you can set it up yourself, and with 20 lines of Python code, you find it in the tutorials, but yes, if you do research on this, it's fine, but if you just want to use it, you don't want to go build it in Python, and you are happy if you have something from the code. Okay, it's done now, so with 3 millions. Okay, what is supported? Let's see vertex patch. Okay, there are some other options. Let's do with this here. Okay, it's also working well. The condition number is 1 divided by log3 about 6. So it's cheaper, but the condition number is worse, and you may need more iterations. But of course, you're asking immediately what kind of patches are supported, where to look for what is supported. Let's try is vertex patch XXX defined, and say it's not defined, and it tells you also what is available. If you have a typo, then it tells you, maybe you're looking for vertex patch, or maybe look for edge patch, all degree of freedom sitting on the elements around the edge, or vertex edge, all doves on edges connected to a vertex, but the vertex itself. If you remember the old times, there was block type 4 and block type 11, and if you do Maxwell, you use block type 11. Okay. Okay, what about static condensation? If you do higher order, you like to eliminate your internal variables. You only want to compute with the degree of freedom on the boundary of the triangles. You compute on the coarser grid only the variables on the edges, facing the B, and for the prolongation, you need also the degree of freedom on the edges inside. But you don't have the full solution on the triangle. You don't want to recover the internal degree of freedom on the coarser grids. You want to go from the coarse grid skeleton boundary here immediately to the fine grid boundaries. And for this, you have no canonical embedding for the functions. For this, you can do something like you do in the reconstruction of the internal degrees of freedom with a harmonic extension. We can solve a local Laplace problem to define the degrees of freedom on the internal edge. So we can do a harmonic extension from the boundary of the coarse grid triangle to the internal edges. Harmonic extension means solving a Dirichlet problem for the problem you have at hand you want to solve. So you say, if I'm solving Laplace equation, so I do a harmonic extension with respect to the Laplace operator. Okay, somehow we have to tell the space which form it should use for the extension, for the prolongation. Okay, we do it like this. Define the space with however prolongation. We build a Balinar form where we do static condensation. So it condenses out the internal degree of freedom. And now we can tell the space, please do a harmonic prolongation by solving local Dirichlet problems coming from this Balinar form. we need first to set up the Balinar form to know to define in which sense we want to do the harmonic extension. And then we can give this Balinar form to the space. Okay, I think a bit worse condition number, also very good condition numbers, eigenvalue between 0.9 and 1. But of course, one iteration much cheaper, then we got rid of the internal degree of freedom. For the whole solution process, we only work on the condensed matrices, only on the finest grid we got the, yeah, it looks the same. Ah yeah, some sugar stuff here, so this is harmonic extension. I think you copied always, I always copied these 4 lines with a harmonic extension and inner solve and Schur complement and so on. Maybe some of you are using the BVP, learned that many people like the boundary value problem solver, where this is done automatically, which is pretty old. We came up now with a more intuitive syntax with a solve Balinar form times grid function should be equal to the linear form. We give this DFT boundary conditions and use a CG solver for it with this preconditioner. So it's a bit inspired by the old generation Phoenix solve, AU equals F. You know what's going on in the background, but when you are in a lazy mode, then you use just a solve function. To see a bit what the harmonic prolongation is doing. Let me come high order space. Okay, I'm interpolating my grid function, draw it, and okay, I have a VI equals mesh. I set it to this function here. Okay, this happens after harmonic prolongation. Yeah. You see, on the coarse grid edges, we get the function from the coarse grid. So you see the sign here, the sign here as a diagonal. But the internal coming from harmonic extension, it solves a DFT problem of this triangle, and of course you don't get the original function you are going to prolongate. You get it only on the coarse grid skeleton, and here you have the harmonic extension.
This is not yet the harmonic extension, right? I think you have 3 plus. The third one should be the harmonic extension, right?
That's the third. Yeah. The third one and the second one look very similar. You're right, the last one is with the harmonic extension on these triangles. The second one is without doing this element-wise harmonic extension. This is coming out of the prolongation. If you have good eyes, you see on the edges, these 2 grid functions coincide. On the edges, we have already the same from the harmonic prolongation, and then in the last one we're solving also the interior problems. You see the interiors are a bit different. Okay, nice, we can solve all the 10 problems now a bit faster than before. But maybe there are also some problems where it's more essential if you can do it. Okay, let's do nearly incompressible elasticity. Okay. Okay, now my Balinar form is grad U, grad V, plus parameter diff U, diff V. Okay, so how about the prolongation? What do you mean with nearly incompressible materials? I mean, I have a large parameter here. Well, if I go up with the parameter, you see the condition number largest divided by smallest eigenvalue is going up. problem gets more and more ill-conditioned. Okay, this was with order 2. If we do it with order 3, big difference. If we do it with order 4, if we do it with order 4, you see the condition number is now independent of the parameter. I can set it also higher. Well, about the same. So with lower order, it's getting worse and worse if I make a higher and higher penalty here. Okay, why does it work for order 4 and up and not for lower order? Okay, so this nearly encompassing materials can be reinterpreted as a mixed formulation with displacement and pressure. The pressure space is one order lower than the displacement space. Now you ask, do we have a stable mixed method? And if you do continuous velocity elements and discontinuous pressure elements up from order 4, it's called Vogelius elements, you have a LBB stable method. It gives you a good coarse grid approximation. And for this, coarse grid correction, multi-grid is doing a good job. Okay, so it's related to this mixed method, so a stable mixed method. Okay, you can go up with the penalty term here as you like, and the iteration number will stay the same. Well, if you have order 4 or higher elements, 3D I don't remember, is it 3D, is it order 8 or something, or 7, 8, 9 or something in this direction. Okay. Okay, here you don't see a harmonic prolongation, you see just the high order prolongation. You really have to do the grid transfer with high order accurate. So you cannot go back to lowest order as we have done before. You have to prolongate exactly your coarse grid, fourth order polynomials to fine grid. Okay, you can play around and but there are also other tricks if you don't want to use high order, if you don't want to use order 8 in 3D, or don't use 4 in 2D. Okay, so that's binomial form, the H1 elliptic problem, plus the upscaled term with the diffu diff v, and you plug in a projection in here. It's like a mixed method where you have the H1 conforming for the displacement, and in the pressure variable is lower than the divergence of the velocity, maybe u is p2, and diff u will be p1, and you project into constants. So you're cheating, you're modifying, you're doing some rational crime, you're modifying your binomial form. The problem is equivalent to mixed problem, and the mixed problem is now LBP stable. And with this you can do a order 2 method. Got u, got v. We can interpolate the divergence of u into a pressure space which is order 0. This realizes this L2 projection in here. And you see it also works. And if you also solve a problem here, okay, it does not like this one. Okay, we solve this Stokes problem with the force going up, right, and get the circulation. And well, 30 iterations, not so bad for a Stokes problem by penalty. Okay, why is this method working? Short two short ingredients. First is you need smoothers, which take care of the null space of the divergence. You can split the discrete divergence function into local functions. Vertex patch is fine for this. a point smoother would not work. And if you have a coarse grade diversion function, going up to the fine grade, you must end up in a fine grade diversion function. Then you are robust in this epsilon. If you have a coarse grade diversion function, meaning coarse grade, prolongated, and you are not diversion in the fine grade, you will see the epsilon in the condition number. Okay, what's a unit square? I have here a bit nicer example. So I build a geometry like this, so a small pipe with open cascade turtle graphics, same H1 order 2 order prolongation, harmonic prolongation. Okay, 5 levels, 200k unknowns. Solve it. This was not too fast. What's going on? Did something change on the syntax? Sorry for this. GFU.
Is the boundary correctly named?
Mesh that boundary is in. We have the in boundary. In or default. Okay, let's run it again. So it. Okay, typical. Tell me if it's working for you and if I have a small typo somewhere. Definitely it was working before and it was running in about 2 seconds. And oh, shit. Yeah. Okay, and you find also computations in this thesis here on page 116. I want to show this here. Okay, go up a bit. And then we find also the solution, how it should look like and how it was looking yesterday. Okay. Here we have it. So a solution looks like this here. It's exactly this pipe here. I have also some numbers in this thesis. Okay, it was this problem with about 200k unknowns, about exactly this P2, P0 elements, and it was running about 4 minutes. And it was my thesis, and it was 24 years ago. No, and it's 4 minutes there, that time, now it's 2 seconds. But it's the same method and similar number of iterations. And it was working on a previous code before NGSolve, but it was never working inside NGSolve, and now I'm very excited that it's now working inside NGSolve. Okay. Yeah, so and there's also the analysis of this method, why it works and why it works robust in epsilon, doing these block smoothers and doing the robust grid transfer operators. Okay, but what do you say to this P2, P0? P2 continuous, P0 discontinuous, Stokes finite element method. It's stable, but it's not the best method. So you're paying the price for second order velocity elements, but you only get the O of H conversions rate to the piecewise constant pressure. And you may search for different methods which allows for the same fast solvers. you want to have discontinuous pressure, and you want to have a balanced method where the velocity order is one higher than the pressure order. And and this was 2000, and not many options were available at that time. And since I was searching for good methods where you can use this fast solver together with a good discretization method. And my strongest belief is that these HDIF conforming HDG mixed methods are the right methods for Stokes, allowing also for fast multi-gate methods like this. Okay, but now the next hustle is you have these facet spaces. You don't have not only polynomial on the edges, you have degree of freedom sitting on the edges. Can we do the same thing also for hybrid methods? Okay, yes, yes, in the next notebook. Okay, what we call hybrid methods? Okay, many people call many methods hybrid methods. In this context, we think of methods having not only polynomials on elements, but also independent polynomials on the edges or faces between the elements. And we have hybrid mixed methods, which come from hybridizing Ravi-Atomar mixed methods, and we have hybrid DG methods where we have polynomials on elements and polynomials on the edges. We have a lot of notebooks explaining this. I'm not going to explain it more than here now. So a hybrid DG method looks like this. So we have a space with element polynomials and facet polynomials. We have the boundary terms, and now the penalty term. And the penalty is, in DG it would penalize the jump between element and neighboring element, and with the hybrid method we penalize the jump between the element term and the facet variable, and we need this term for consistency. And the nice thing with this hybrid DG in contrast to DG, we can do a static condensation of the element variables, can reduce the problem to the facets only, which is a system of much less variables. And we want to solve only for the facet system, and then at the end we reconstruct the internal variables. Okay. Check. Let's see if it's working. Yes, it's working. So we solved 500,000 now. Condition number, wow, also between 0.9 and 1. So what do we do here? So we have the product space, polynomials on the elements, polynomials on the facets, the harmonic prolongation, so the HDG binomial form, as you know, harmonic prolongation, and multi-gate with the vertex patch. Okay, what's going on here? So it does the high order prolongation for the facet space. So I have the coarse triangle splitted. We have polynomials on the boundary of the coarse triangle, which are canonically prolongated to the fine grade. There's the short edges. We just take the polynomial from the coarse to the fine edges. And you have the internal edge. By subdividing the element, you have to somehow define the polynomial on the internal edge, and this is provided by this harmonic prolongation. On every level, we have only the condensed matrices, and from them we can solve local Dirichlet problems to define the polynomial on the internal edge here. Well, working fine. If we solve a problem, yeah, fine, looks good. Also small details. If you do a mixed formulation for hybrid mixed formulation, you have a HD flux and a L2 state, and you are breaking continuity of the Ravi-Atomar elements, and you have a Lagrange multiplier to make it continuous again. So you can condense out all internal variables. You can also go to a problem on the skeleton. Okay, we have a discontinuous HDIF, and we don't want to have says the flux show up in the final system. We want to have only the condensed positive definite system, so we make it a hidden space or a private space. The mixed binomial form diff sigma times v plus boundary terms from the Lagrange multiplier condense everything and working the same. Did I? Okay, you can do some post-processing. Okay, now it's a mess. No, it's fine. Okay, and scrolling. Okay, why did we do this hybrid DG hybrid mix for a Poisson equation? That means it's some kind of overkill, so we can solve with conforming methods as well. But now if we do nearly incompatible materials, vector H1 with a big diff term, we can now do these balanced good elements, having order k for the vector variable, k minus 1 for the pressure, and this is a method which provides also the robust prolongation and localization of the null space. This is the method of Christoph's master thesis, where we started with this HDiff conforming HDG methods in the joint paper. You find also the highest order DC discontinuous trick, where you reduce the facet order by 1. Well, and okay, not that good condition number as for Laplace, but condition number 1 divided by dot 7, iteration numbers. Oh, I'm not drawing it. And you can do it also in 3D without going to order 9. So we're doing a cube now, second order, HDiff, high order prolongation, tangential space. Okay, 2 levels of refinement, 90,000 and 8 times more than 700,000. And solving such a nearly incompatible material problem. Okay, we can also call it a Stokes problem, Stokes by penalty, making it divergence free by this big penalty term. Penalty was set to okay, penalty set to 1000. Okay, 50 iterations. It has now a circulating Stokes law on the cube. Okay, now this is now my favorite methods for discretizing Stokes, Navier Stokes, and using this kind of multi-grid solver. Okay, you can do it if you not only have the fine grid, but you have some small quantity discretization, and you have some memory left for doing 1, 2, 3 levels of mesh refinement. What you often can do for flow problems. Geometric multi-grid is, I think, a valid option there. For example, this iteration number is independent of the shape of the domain. It only depends on the element quality. If you have very elongated domains, in the LBP condition maybe become back. If you do this block preconditioners, they suffer from bad LBP conditions. But this only works locally. It only depends on the shape of the elements, but it's robust. It's better to the shape of the domain. So. Okay, this was part 1 of my things I wanted to show what is new. Some comments, questions on this part?
I found a mistake. It was my fault in the other notebook. The syntax. You can just change the last thing to not use the pipe operator, but make a mesh.boundary CF.
Ah, okay. That's what the fixes from
I fixed it
the
now
last
already
days. So
here, but then you need to rebuild. But
Okay.
you can do it.
so instead of this one, I do.
Instead of this, you do mesh.boundary CF from this coefficient function.
Hmm?
No, usually equals mesh.boundary CF.
Ah, boundary CF
Yeah.
on
And then dictionary
in.
this. Yeah.
Maybe.
And default is 0, 0. Right, some
Sure.
brackets are not right. With the
closing bracket after
closing bracket from the map, yeah.
all cows.
Default should be string, right?
As a dictionary,
The dictionary
it
bracket
stops
is
here.
not-
Yeah, now we.
Sorry.
And we made a NGSolve and it recognizes. Yeah, it solves in 1 or 2 seconds, and you up. You see the absolute value of the velocity. You see the flow through this pipe.
And the other syntax works when.
And then when I do the next update.
When do you do the next update?
Okay, thank you. Okay.
Higher order prolongation works only with bisection, not for other.
Okay. Yeah, correct. Yeah, that's. Okay, so this prolongations precomputes a prolongation matrix for a reference element, and the reference element is not one reference element, but for a class of elements using this vertex sorted orientation. So for every possible permutation of vertex indices of the course plus a new one stores a new prolongation matrix. In 3D it's factorial of 5. For the other prolongation it has to take also vertex indices inside, so there are 10 vertices, so it is factorial 10 prolongation matrices, which is quite some considerable memory for the prolongation matrices. And the advantage of this bisection is you can do also adaptive refinement. Disadvantage, it's not yet running in parallel, it may come also in parallel, if other problems in parallel are resolved. So, and it should work for all spaces from the DRAM sequence, for which we can convert it to L2. Scalar, vector, matrix valued L2 functions. Since the prolongation is much easier for the element-wise polynomials, for the discontinuous spaces, we also transfer it to this. And for facets. For facets it's also implemented for the L2 triangles on the faces. Okay. Can I stop with this? And this high order prolongation may become default in the future. Okay, what's new also? Oh, it's not here. The other part I mentioned already yesterday that BEM is now included into NGSolve. At least, so we started last year with, a half year ago with Lucy Wegler to add a boundary element code on top of NGSolve, which was an external package, and now part of it is merged into the NGSolve core code. It's much easier for me to work on it and also to maintain it. But I assume you know as much about boundary elements as I knew 2 years ago. I still know that. you have this carry operators, a V as a single layer and double layer and axis, and put them together, and somehow you get something out of it. And it's cumbersome since you get dense matrices, and you have to do something to speed it up. So you do these H matrices. Okay, there are two major players on making it fast. One is H matrices, one is this fast multiple method. I'm not on the. Okay, both have pros and cons. Now we have the fast multiple inside NGSolve. Okay, what is the idea of this fast multiple? Okay, you assume you have far distance interactions. You have many particles here, and they interact with particles here, like gravity. You have many point masses here. You have n point masses xi, yi, and you want to evaluate this gravitational potential on many points y, xj, on m points. And if you do it naively, you have n times m operations. And the idea with fast multiple is if you have here many atoms and you are far away from this from the sun, all these point masses here have similar effect if you're far away. So you can glue it to one mass and use it just at the center of the mass. But if you're not so far away, gluing it to one mass is maybe not enough, certainly enough, accurately enough. But you want to do a series expansion of them. You want to do a series expansion of 10, 20 terms here, which takes the effect of the million point charges of the atoms of the sun. Okay, it's a famous algorithm. It was selected as one of the top 10 algorithms in the last century. Gringard, Rochlin are the inventors of this. This is one big school of it. And starting it, I recommend a book by Gomero from Turaiswamy, where I learned a lot of this, also technical stuff of getting this multiple also running practically. Okay, let's start with the very basics before going to BEM. Okay. Okay, here I have this interaction is based on some interaction kernel. This is this 1 over distance for a Laplace equation, and if we do Helmholtz, it's 1 over distance times the spherical wave function, I wave number distance. Okay, implement this kernel function, just the distance and the exponential function of the distance. Okay, we are always doing 3D problems now, but looking onto the solution on, or the function on a phase. Okay, here is this point radiator, a point source, oscillating, and you see the solution of the Helmholtz equation with a point charge, the Green's function. Okay, now I don't have only one charge, but I put 3 charges now nearby, and you already see they look similar, but you also already can imagine some radiation pattern. You have a better positive interference in horizontal direction, but you see a weaker field in vertical since there is some cancellation. Or even more, if you put 2 charges with opposite sign, then they compensate exactly in horizontal direction, and you see only this radiation with this direction in with strong components in vertical. Okay, and if you put 2 charges closer and closer and make them larger and larger, you have something what's called a dipole. Two charges, two poles. In the limit, you have a dipole source in a common point. Or if you put 4 charges close together, you may get more and more funny radiation patterns. Okay, this is direct evaluation. We have 4 charges, evaluate the functions just by the slow algorithm. Okay, what we have now is a multipole function, which allows us to combine several charges to a series expansion of their common effort and evaluates their function, the potential of all these charges together. Okay, so I define a singular multipole coefficient function. I provide the frequency. I give the number of terms in the expansion. So I have 10 order 10 terms, order 10 in the expansion with a center in the middle, and I'm adding several charges in points nearby. And we see more or less the same as we have seen before. But if you look carefully, it does not look very nice inside here. It's getting worse again, so I put the charges in a larger distance. So we see the function looks nice further away, but nearby it looks like a divergent series, and it is a divergent series. So we have the series expansion for the sum of this thing, Green's function, dipole, quadrupole, multipole, and the series converges if we are outside the distance of the largest distance, but it diverges if we are inside a sphere. The radius is the largest distance of the charge we added to the multipole, and it's clear that it must diverge here. It's not a bug. Okay, now I put many charge. No, I put 1 charge. I did it with a bit higher order. So now the charge is several wavelengths away from. I put the charge source here. You see the divergent multipole expansion, but outside this ball, this 3D ball, the solution looks nice. So the series converges, and the farther away, the faster it converges. Okay, so I defined my multipole here. I said, in this radius I may add point charges, and I guarantee that the solution, the series converges certain rate outside this radius. Outside this radius, I can now use this solution of the point load. Okay, and with this multipole, there are 2 types of expansions: a singular and a regular expansion. The second one is a regular expansion. What you see here is the same function represented by a different series expansion. So it's now a series expansion centered here, and the convergence is now inside a ball. Inside a ball, and it diverges outside. One is like you may think of a Taylor series and a Laurent series. And so what we have done here is I set up a singular multipole coefficient function here. I'm putting charges into this multipole. So when I do it's a charge, it computes its multipole coefficients for this series. And then I convert it to a regular multipole coefficient function. Okay, I make a regular multipole with 40 terms in frequency centered at the point x5. And we can transform expansions from one function system to another function system. That's an important operation. So I have the multiple expansion here, centered in the center, and transform it to a series centered here. Okay. That's the first. This is a multiple expansion, not yet a multi-level or fast multiple. Okay. what are the kind of basis functions you need? Yeah. Okay, so I'm talking about Helmholtz equation now. You have a singular expansion and a regular expansion. Okay, and it's a kind of it's a Treff's method. You write down solutions of the Helmholtz function, and it's easy if you have if you have spherical coordinates. You need a basis on the sphere and a function in radial direction. Okay, on the sphere we need an orthogonal system with the spherical harmonics y and m from an L2 orthogonal basis on the sphere. And now we can solve Helmholtz equation inside. So for every basis function here, there's a solution like separation of variables. If you do Laplace transfer square, you have sinus times sinus hyperbolicals. You also compute the function inside the ball. Or you can take the function on the boundary and solve the exterior Helmholtz equation with a radiation condition. And the functions in radial directions are Bessel functions, first, second kind Hankel functions. You can you read it up? Okay, actually, so we have this double sum here. If we do order 10, then we have 10 squared basis functions. Since we are discretizing L2 on the sphere, a 2D manifold, so we need order squared many terms in the expansion. And he said order 10 before, we had 100 terms in the expansion. Okay, what does this spherical harmonics? Okay, here's the definition. How does it look like? Okay, for demonstration, we can plot the spherical harmonics basis function also on a sphere. Okay, they are complex valued functions. They are e to im. So we have spherical coordinates with the azimuthal angle and the polar angle, Längengrad and Breitengrad. E to im phi is the longitudinal angle. It's a complex trigonometric function. We can do an animation and we see it's rotating. And this is for two functions, so it has 4 peaks in the longitudinal direction and 2 peaks in the polar direction. And they are an L2 orthogonal basis on the sphere. What are the functions in the radial direction? They are this Hankel and Bessel function. That's a Hankel function, Bessel, first and second kind, and you can write down the first 2 terms. And then you have a recurrence relation. The first 2 terms, and you have a recurrence relation, whereas in theory where you have defined all the functions. This comes out by doing the separation of variables. The big part is, okay, first how does it look like? Python has them. Okay, somehow they look similar. So blue is the Bessel, orange is the Hankel. You see they're oscillating. Okay, so they have the behavior of the Helmholtz equation. This is order Bessel-Hankel function order 50, and you see precisely at 50 they start with the oscillation, and below they are different. The Bessel functions are very, very small. It's like x to 50, and the Hankel is like x to minus 50. So very extremely small, extremely large. And it's tricky. You learn in special function books how to evaluate them. This 3-term recurrence is not good for evaluating the Bessel functions from the small to the high. What you have to do is you can go from the high to the small and do the recurrence backwards. You check where you end with the first one and rescale it. And then you learn that if you do it, you are reaching the floating point limit, so e to 300, and you have to do your own floating point arithmetics to get it stable. Some fun with this last summer. There's this FRM 3D package where I could learn a lot from what are some tricks to implement it. Okay, these are the building blocks for building such multiple, the singular and regular multiple expansions. Okay. Okay, you may have heard about layer potentials. Okay, if you put charges on a shield, you are integrating over the shield charge density times Green's function, and you evaluate this away from the shield. So the V, the single layer potential, S rho, is the integral over the shield, Green's function times charge density on the shield. Okay, it's a single layer potential. We want to compute this now. Okay, we have two independent measures, one vertical, one where we have the charge density, the other where we want to visualize. Oh, I didn't, yeah. Okay. Okay, what we see here is that the visualization on the horizontal mesh. We have the source plane is vertical here, so I put a charge density onto this shield. And I'm integrating over this vertical shield. And with integrating, I mean doing sum over elements, sum over integration points, as we do the integration with FEM. Okay, here you see how we can do it in Python. So we are picking an integration rule for triangles. We are mapping the integration points to all triangles in the mesh. So we get now points in physical coordinates. We can evaluate some function, it's the one function here, you can do this or whatever you like, in all these points. Okay, now we do the numerical integration by hand. So we're doing this transformation and integration weights. So we're getting a lot of integration points on the shield. And these integration points are all charges for our multiple expansion. So we add in the integration points, we add function times integration weight. So we have now, okay, 30,000 charges on the shield. This means we want to have a fast evaluation for many, many point sources. Okay, and you see it here as the sources, and you see it looks good also not only outside this convergence ball. This is why we have now a multi-level multiple coefficient function. And multi-level means we have the large multipole, you have an octree, you're going down to smaller and smaller balls in a hierarchical way, the octree. And if you're near, you're using, say, multipole from smaller trees. If you're far away, you're using multipole from farther tree. And we can do this multi-level multipole, the singular multi-level multipoles convert to a regular multi-level multipole. We have regular expansion on the large balls, which has many terms and is expensive, but you can convert it to smaller regular multipoles, which allow faster evaluation. Important is this transformation from singular to regular multipoles, where most of the operations happen. And now the evaluation, you should see the same function. The difference is small, it's 10 to the minus 5 small. But now with a representation in this regular function system. Okay, this is a single layer potential operator. If you look at this, how does it look like? Okay, well, where is it best? Oh yeah, it's okay. You see a function here which is continuous over the screen, but it has a kink in the derivative. And then there is a single layer potential operator, there is also a double layer potential. And this comes from taking the normal derivative of the Green's function, it ends up with this. And double layer, so what does it mean? So it is like if you put a charge density epsilon in front of the layer, a negative charge density epsilon behind the layer, of opposite sign. So you're producing a dipole density. So you have a double layer, epsilon before, epsilon behind, and you send epsilon to 0. But this difference quotient, you get the derivative in normal direction. So this ends up in this integral operator, which is called the double layer potential. Doing the same thing, integrating over the shield, and now to the multipole we can now add a dipole. What means a point, a direction, the normal vector, and a dipole strings. Very similar thing, and the function we see here now is we see it's discontinuous across the shield. This double layer potential gives us a discontinuous function, but the normal derivative is continuous, opposite to the single layer potential. You see it does not look nice since the shield mesh and the visualization mesh are unrelated, so you get some regions where you evaluate and interpolate. Okay, well, we don't want to do this integration point stuff always in Python. We can also directly add a charge density. If you want to do this, you have to update to the version from today. Recompile. Okay, so we're adding a charge density value 50 on this region, and it does the integration internally. It looks the same. Okay, now we are given the charge density and evaluate the single layer potential. We know the function outside here satisfies the Helmholtz equation, and we are given the charge density. But now we want to solve some problems. We want to find a function which has prescribed values on the screen, having potential 1, Dirichlet boundary condition at the screen 1, and the question is what is the charge density? What charges do we have to put to obtain a single layer potential of a given function on the screen? Okay, we are given an U0, and you want to find a charge density rho, such that V rho, single layer potential, in a rational sense, is the same as the given function. Okay, now you remember this layer potential was already an integral operator. Now you have double integrals, typically in x and y. With double integrals, you can, and what you have here is a binomial form. It's linear in the function rho and linear in the test function v. You can do what you know from FEM, you plug in your basis functions, you get the matrix. But thanks to this double integral, you buy in a lot of new troubles. It's a dense matrix, so if you have 100,000 basis functions, you have 100,000 squared entries. You have huge matrices, dense matrices. For this, you need compression of the matrix, fast multipole, H matrix is an alternative option. And the second difficulty is you have to evaluate singular integrals. The x and the 2 points of the integration may come close. If you evaluate the Green's function in x and y and integrate over the same domain, you have to take care of the integration of the singular integrals. And here it was really great to have Lucy as a teacher for boundary elements. So, okay, so in this community it's well known there are integration points which treat the singular integrals more or less regularly as a 4D integral. Everyone in this community says, you're using Sauter-Schwab numerical integration. These are the two techniques we need for this. And now we can with an object single layer potential operator, which computes us now the matrix coming out from this discretization of the single layer potential. It does some computations and some setup and provides a matrix vector product. We can use CG to solve it. Have the solution to the multiple evaluation and we see we got a function which has value 1 on the screen. And now we can also deform it. And you see a kink function. You see the function is continuous and it has a kink at the screen. Okay, there is the last one, the Biot-Savart. We can do this also for Maxwell equation. This is Biot-Savart representation. So if you know if you are in R3 in free space, if you know the current density, you can form this integral. This gives you the magnetic flux. It gives you a vector field H such that curl of H is a given current. Right inverse to the curl. And you can integrate along a wire, doing a one-dimensional integral, or can have also a volume charge density, volume current density J, integrate over a volume. And it's the same idea. We can do a Biot-Savart singular multi-level coefficient function, and we can give a current path. So we're giving 4 straight lines, starting point, end point, with a rectangular wire path, adding this to the multipole, going from singular to regular expansion, and we see the magnetic field going around these line wires. Or also look at the field values in the clipping plane, and you see far away a smooth function from this integral evaluation. So this can be used for doing field simulation in a transformer where you have a current path, compute this solution in free space R3, which does not satisfy your boundary values, and then you have to do the FEM problem by using the misfit of the boundary condition to correct the free field gain function. You don't have to resolve the currents, the wires in the FEM mesh, only you need the action of the wire source on your final element boundary domain. You can add also as a current density. And, okay, I don't know where it is computing now. Let's try. Okay, so I'm happy that I survived that long. Okay. Game. Yeah. Yeah. I got what I want. Okay, these are the field lines from this coil source density, and it gives a magnetic field in R3. You will see the field lines are leaving the box, so there are no tangential or horizontal boundary conditions that we use with the FEM. Okay, one. Okay, this was the idea of this fast multipole method. This realizes these boundary integral equation operators. I had shown the notebook yesterday that you can do this for FEM-BEM coupling. You can do BEM only. I'm skipping over this, but I only show unit 11.3 for Helmholtz, where I think it's really powerful. We're doing exterior scattering, solving Helmholtz equation as exterior domain. It's a called Bragg-Hage-Werner formulation, kind of Burton-Miller. They do a combination of single layer and multi-layer potential, which gives you an radiating dipole. It's like an impedance trace boundary condition. Okay, let's run this. Just run it. right hand side. So okay, it's doing sometimes it can. Okay, this is the potential we're computing on the sphere. On the, okay, a plane wave is coming in, scatters from the sphere. This is the kind of charges we are computing on the sphere. Evaluate the potential operators to get the solution on the screen. And what we see, we compute the scattered field, looking like this. And if we visualize the total field, the incoming corrected with the scattered field, we get this X0 Helmholtz solution. You see it's reflected in front, you see the shadow behind the sphere. These are now 5 waves on the sphere, but this method does not need a lot of memory at all, so I could do a scattering with 80 wavelengths on the sphere on the laptop with 16 kilobyte RAM. But this is quite huge, what I could not do with any other method before. So I think for scattering problems, this BEM without multipole is really the way to go. Okay. So, okay, we have included this multipole into NGSolve. There's still this external package, the NGBEM add-on we started together with Lucy. There are more compression techniques. There's also H matrix, which is sometimes faster than the FMM. But it's good, I'm not really overseeing it, and I have difficulties of maintaining it, so it stays in the extra package. If you want to try other options, use the add-on. If you go with the internal, use the FMM. You can do the same things, sometimes this is faster, sometimes the other. There are more tutorials explaining how to solve PDEs with single and double layer potentials and BEM coupling. There's more explanation in Lucy's documentation than we have in the tutorials now. But it's ready to start playing with it, and more is going to come in the future. Okay, so these are mainly the new things I wanted to show. I want to show some other questions of BEM. Otherwise, I'm picking some random examples and I think what could be interesting. Okay, I put also a link into the Google Docs to a presentation from last year at NGSolve, showing some of the usual examples. One I have not shown this one, the Sydney shell. Okay, we have these shell methods which are, Miles has shown on the morning yesterday. Okay, you can do shells on simple cylinders, or you can start with more complex geometries, mesh them, also with boundary layers, put the shell method with this H-diff methods, so you simple method, just put it on curved boundaries, compute, and you get also a deformation of this very complex shell. Does this mean that I like the kind of methods which work for the simple domains, but also if you have a complicated problem, it takes the same method and it also can be applied there. Yes, I want to show this one here. Why? What is a nice thing on H-diff conforming? Okay, let's go. I was thinking to find out also a bit about history of NGSolve and domain morphing I want to show. Okay, yet another channel with a hole in it. So HDIF conforming HGC for neighbor strokes. This is a flow going around this cylinder. And now as is, I want to bend this pipe. So I'm deforming the geometry. And you see immediately the flow following the deformed geometry. So when it was going in the x direction before, after bending, it's going straight up following the pipe. And this comes from using the Piola transform for the velocity space. So when you move the domain, immediately the flow is following the new geometry. And it's immediately divergence free also on the new geometry. I can also move the lower bound, upper bound, make it wider, thinner. Okay, you see the channel is wider here now. With the Piola transform, the function gets smaller, so the same flux is going through this, the same total flow flux is going through this wider part of the channel now. Okay, you can move the upper part, and you can, so it's getting thinner, so the flow immediately gets faster, and you can make it thinner and thinner, and sometimes simply you crash the time stepper. Okay, so it's a nice argument for these HDIF conforming methods. These were students they did a seminar work and they looked at the Christoph narcissism and learned it from there and got some code snippet and could set up this morphing domain part. And another thing I want to show is fast explicit time stepping. Okay, doing a wave equation, pressure, velocity, time derivative of one is the diversion of the other one. We set up a mass matrix for the pressure, mass matrix for the velocity. You have the matrix of the gradient, transpose gradient. We want to do cheap mass matrices coming from discontinuous spaces, so doing DG, classical element-wise DG. So the binary form looks like this, so it's gradient pressure times velocity, facet terms. And the nice thing is, if you do the proper mapping from the reference element to the physical elements, the element matrices on all the elements of the mesh are the same. So we can do this with computing only the element matrix on the reference element and using the same matrix on all the elements of the mesh. We can do a so-called geometry-free matrix. Okay, this is my domain. So it's a cube with a cylindrical hole. I'm setting up an L2 space. I'm setting up the vector L2 space with the proper mapping. So with L2 I could do just a one-to-one mapping, but I want to do an L2 where to use the Piola mapping. Then the transformations cancel out. I'm setting up the grade P times V matrix. I'm setting up a boundary matrix. I'm setting up a matrix for the facet space. I have a trace operator which gives me the trace of a volume function at the boundary. So these matrices here are not really matrices, they're linear operators. You can do a matrix vector multiplication with them, but at the first glance you don't see what is the implementation of this matrix. You can add the linear operators, you can add them and compose linear operators. L2 provides also cheap implementation of mass matrices and inverse mass matrices without any matrix assembling. And I let now a 3D wave problem running, so I had the source here. I think it's for a 3D wave problem, it solves pretty fast on the laptop here. I'm drawing only on the surface. You see the scattering on the disk here. Okay, then stop this. And we can do this also on GPU devices. So we import NGS CUDA. It's in the release here. It's not here, my laptop. And you can run the same on the device. So we copy our starting vector over there. We are moving the, okay, so P is this linear operator, this combined linear operator. We have the inverse mass matrix. So we have this whole combined operator. And we say, okay, please send it to the device. Then the whole operation is stored on the GPU. We copy the initial values over there. We copy back the vectors for visualization, but all data stays on the device. Okay, it's now running on my fake GPU. Okay, what we copy over are linear operators. Okay, so, and now we look how these operators are implemented. So we are looking at operator 1. Operator 1 is time step times inverse mass matrix composed with the gradient matrix. And this is the dynamic storage of this composed operator. So it's a product matrix, what is a composition of two linear operators of this dimension. Scale, this is a time step. You have the sum of two operators. So this represents a composition of operators. And in the leaf, we have just a few operators. So we have a block diagonal matrix, so the structure of array. We have a constant element by element matrix. This means we have an element matrix constant for all elements in the mesh. So we're only storing the row and column indices. So we have maybe a handful different types of operators. The whole DG time stepping is represented by these operators, and which we can send on some compute device. Now it's a single GPU, maybe some others in future. And on an A100 it runs about 10 times faster than on a single PC. What else you can do with this technique? You may have seen this split ring example. We do a wave equation on a nano-optical device like this. Yeah. Yeah, we have a strip, a waveguide up here, so we have a source there. Due to the dielectric properties, the wave is confined to the waveguide. Now you see this ring also, which coming pretty close to the strip, and you see some part of the wave is tunneling over to the ring and continue inside the ring and turning around in the ring. This is one of the standard nano-optics benchmark examples. You see the one wave is passing to the exit at the top strip, and what this we want to have proper boundary conditions, absorbing layers, that the wave is not reflected but getting absorbed by the PML layer. So in the thin layers there you see the time domain PML. Time domain PML is realized by coupling additional fields, getting and solving ODEs in the points outside, and you see the wave is pretty much absorbed here. And the whole thing is we have some more complicated equation. We're adding some more terms from the PML. There's a link for the reference how it works. But at the end, it's only setting up a couple of more linear operators with a few more terms. But people who work on the theory of the PML can write down the equation, and people who are more in the optimization and want to bring this to devices work on the handful matrix classes. Okay, and I think that's now the good time to stop. if you are interested in particular topics. That doesn't. And now, coffee break.
Jan, kannst du noch hinzuschieben? Ja. Danke.
Nicht die Warte einsprechen.
Bitte? Okay, so after these all new features that we have learned in the morning, the next session is on NGSolve. Big package, I think. Yeah. A big package. That's and please, at the beginning of the lunch break, I have some announcements. So please stay here and don't run to the coffee or wherever. Thanks.
Okay, thank you, Philip. Yes, we're here to present the NGSolve package. So these are drafts methods in NGSolve. Yes, the part contains of work done by Samantha, Philip, Christoph, Johan, myself, and Igor. As on the slides, I will present a short introduction to draft methods, and then Igor will continue with some examples, and Johan will present a novel idea, the conforming draft methods that we recently came up with. So, I want to invite you to follow the talk along on your laptop, so you can try out everything by yourself, ask questions. We have a bunch of examples in here. It's very easy to install, so you can simply use pip install NGS drafts. Should work even on Windows. The source code, of course, you can find on my GitHub. And there's possibly also a hands-on session tomorrow if you want to dive into the C++ side of things. Everything else is, of course, on the Python side. And then the material for this talk is in the cloud that Philip provided in the email. There's a shorter link because Philip was so long. If you want to copy this link or follow the link on the email, you can open the slides. It's a simple Jupyter notebook, and follow along during the talk and run all the code yourself. While you pip install and open the slides, let me just tell you a bit about the package. I started working on the package in the beginning of my PhD that I did in Vienna with Ilaria Karucha. That was around 2018. And then when I did my postdoc, my first postdoc in Göttingen with Christoph, started around 2021. For 2 years, you can see we continued development and got really excited about this embedded drafts method that we then implemented. And very recently, Johan implemented a big part on this conforming drafts. You can see this daunting pull requests of 60 commits that I got in single out a day where I had to merge this pull request. Yes. So the development still continues, and we have a bunch of new methods and small little things to show from the last user meeting. Okay, are there any questions on the installation? Is everyone who wants to follow along ready to go? Then I will continue.
The link to the material is now also in the docs file, so there you can. Sorry.
Sure. Okay. So yes, what is the name of the game? What is the general idea of a drafts method? So we're talking DG methods. So we have basis functions on each element, discontinuous across internal boundaries, and the conformity is weakly enforced inside the bilinear form, right? And what we want to do in drafts methods is to, instead of taking the full polynomial space on each element, take a smaller subspace or a smaller space that has the same approximation properties as the full polynomial space that we see from polynomials, but uses few degrees of freedom globally, right? So, and on each element. So, the most basic idea, why does this draft space retain the good properties, but is smaller? What we want to enforce is a condition like the one you see on top here, where we are in the kernel of our operator. Yeah? So, thinking of the Laplacian, this would simply be, if we want to solve the Laplace equation with right-hand side 0, we want to approximate our solution with harmonic polynomials instead of the full polynomial space. It's a basic example. This is simply implemented in NGSolve using the drafts FA space instead of the L2 FA space. If we want the harmonic polynomials, we can ask for the equation that we want to try to solve, like the Laplace equation, and then this space will generate us the harmonic polynomials instead of the full polynomials. And if I run this code, you can see of order 6 on this simple mesh, we get 312 degrees of freedom compared to the full L2 space, which holds 672 degrees of freedom, right? So yes, we have a great reduction of degrees of freedom using this space. Of course, this comes with a bunch of caveats. So we need to construct these basis functions, which is difficult, and for some equations that involve varying coefficients or a right-hand side, yes, this will give us some trouble. Then for other equations like Helmholtz that have like a mass term, these functions are not polynomial anymore, but instead made out of plane waves, which are prone to ill conditioning and very troublesome. So yeah, we might want to do something else. Okay, so here's just to finish my quick example. We have these harmonic basis functions. Here's the basis. And quickly you'll have a look at the basis. So we see the constant function, x and y, the two linear functions, which are of course harmonic also. But then instead of continuing with the normal monomials, we have the function x times y, and then x squared and minus y squared, which is the harmonic part. You can see here the nice curvature on the element. Yeah. So this is just a basic example. And of course, we can use this space in a simple DG bilinear form. So this is the standard DG bilinear form that you would use in NGSolve. You simply replace the L2 space with the Treff space, set up a bilinear form, solve as usual, and you can get to this standard solution with about the same approximation property like the full polynomials, right? And again, just to visualize this, the reduction of the degrees of freedom. On the right-hand side is the sparsity pattern of the L2 space. So we're just using more degrees of freedom on each element, while on the left-hand side, we are now using this Treff space. So we have the same sparsity pattern, of course, since the coupling is exactly the same in the bilinear form through the elements, but we are using way fewer degrees of freedom, so the global system matrix is just smaller. This is the matrix that we have to invert, right? Okay. So now to my overview on what we want to present today. So I've just given you the basic idea of Treff's methods, but as I was saying earlier already, while these basis functions are in the kernel, we have troubles dealing with the varying coefficients or with the right-hand side. We have to implement these basis functions, so we have to put them explicitly into our code. And this is the standard Treff's machinery, right? And there are two ways that we have to expand this to varying coefficients on the right-hand side. Okay? So what we want to do, the main idea going forward, is instead of using this standard Treff space, we want to relax this condition a bit to allow for varying coefficients in our equation or have polynomial functions, even though we have an equation like Helmholtz. So we have two methods, the quasi-Treffs and the embedded Treff's DG method, that instead of using these functions that adhere strictly to the kernel, relax this condition a bit. So I put a tilde on this basis is in the kernel. We are not in the kernel anymore, but we are very close to it. And with this, we can deal with the varying coefficients and right-hand side and still get the same reduction that we see for the Treff's method and have good approximation properties nonetheless. Now, we still have the issue for the quasi-Treff's method that we have to construct these basis functions by hand. So we have an additional cost of a Taylor expansion of the varying coefficients that we have to do. And then we have to construct this basis basically with a recursive algorithm inside our code, and the Taylor expansion can be somewhat cumbersome or slow in some cases. So what we're currently more excited about is the embedded Treff's method that allows us to avoid this explicit construction. So while I put a red X on the explicit construction, this is actually a feature, not a problem. So we avoid the explicit construction. The additional cost that we have is the element-wise single event decomposition that gives us the embedding, as you will see. And this allows us to completely avoid the explicit construction. We don't have any troubles with conditioning anymore, and we get a very nice Treff basis. So in the following, I will briefly talk about the quasi-Treff part, show you how this is implemented in NGSolve, NGSolve, and then we will continue mostly or only with the embedded. Okay. So I have only one short slide going over quasi-drafts. So, as I was already saying, the idea of quasi-drafts and embedded drafts is to relax this condition that we have in the space. And the relaxation differs between the two methods. In the quasi-drafts method, I was already saying, we will use a Taylor expansion. So the idea is, instead of wanting our full operator to be the kernel, we will relax this condition by putting a Taylor expansion there and enforcing this on the midpoint of a point in the element of the Taylor expansion of the operator. We can also put a right-hand side there and then get a particular solution to homogenize our system. Now we have implemented this in NGSolve, but of course only for explicit, for certain types of problems. For example, we have this for the elliptic case. So given any elliptic problem, you can provide the three coefficients there, use again the Drafts finite element space, using the equation type quasi-Drafts elliptic, pass the coefficients, then we will throw on a recursive algorithm constructing basis functions for this Draft space, like so. And then this space again can be used like the L2 space to set up a Bernoulli form and so on. And in order to solve a problem with the right-hand side, this is what we will do with embedded drafts as well, is to get a particular solution. So let's say you have a right-hand side in the problem that is x squared plus y squared. And we can construct a particular solution that will end in the, is an L2 polynomial basis function basically. And then we can homogenize our system. So we want to solve instead, again, the system on the draft space with a right-hand side. And then we homogenize by subtracting the particular solution there on the right-hand side. So we split our solution into two parts. A drafts part, which will be a global part that we have to solve for, and a particular solution that is computed completely local on each element. Okay, so much for the quasi-drafts idea. Let me now switch to the embedded drafts method. All right? So, again, we will relax the condition in the draft space. This time, however, with an L2 product, so to say. So, we will test our condition with a certain set of basis functions, which test functions, which are usually on a smaller subset of polynomials. And this will allow us to construct an embedding, in the sense that we will represent all the basis functions in this space using an embedding matrix, element-wise, T, from the full polynomial space. Okay? Once we have constructed this embedding matrix on each element, we can then solve the much smaller system once again by simply embedding the DG matrix, the standard DG matrix A, into the draft space, and then solving with this much smaller matrix TAT for a solution in the draft space UT. Okay. Again, we have the same idea to put in a right-hand side. So we can homogenize the system. But first, yes, I should talk about how we implement this exactly. Yeah. So the embedding matrix T, how do we get it? Yeah. This is where the SVD that I already mentioned comes in. So the embedding matrix is simply computed by taking our equation, L of U tested with a subset of basis functions in Q, computing element-wise this singular value decomposition, and then looking at the embedding matrix for the kernel of this SVD, right? So the kernel of our operator, the embedding for this is then given by this part of the SVD. This will be our matrix T, and this will embed transform our full polynomial basis, or the part of our full polynomial basis, into the draft space, right? So how is this done in NGSolve? We set up this operator. Yeah. Readable. Yeah. Shouldn't mark it. We set up the operator for the Laplace equation, but this goes similar for all equations, as we'll see in the examples. We'll take a minus Laplace of u, u in our underlying L2 space, and test this with a suitable test space, which turns out to be the polynomials of order -2. Yeah? Of course, why is this the case? Since if this maps directly into the polynomials of order -2, So these are exactly, will test exactly to be the kernel of the Laplacian. So for the Laplaces will still give us the harmonic polynomials. For a more involved differential operator, we will still find something suitable, but different to the harmonics. So setting up this operator, we can pass this to the class of the Trefts embedding. And this embedding will then compute these embedding matrices for us. You can see on the right hand side as an example, for each element in our mesh, we get an embedding matrix. This is the global embedding matrix. But as I was saying, these embeddings are computed locally. And this embeds the full polynomial space, which is of this size, into the smaller Treft space of these degrees of freedom. So yes, this is on each element. We simply multiply these rectangular matrices to embed into the smaller Treft space, right?
Project.
Project, yes, project. Yes.
Is the lab a special operator?
This is simply from hashing. I mean, I used your hashing
Okay,
operator.
yeah, that was the question.
Yeah, it's nothing fancy.
Yeah.
Yeah.
So you can use them.
Okay, so this is what the Treft embedding does for us, and we can pass a bunch of operators to this, and we will play around with it in the next section. The only part, yes, I want to show is how to deal with the inhomogeneous problems. I've already briefly discussed this for the quasi-Trefts case. It is very similar here. We have already computed a singular value decomposition on each element, right? So to get a particular solution on each element, the game is simple. We take the pseudo-inverse of the SVD that we have already computed and pass the right-hand side. So the pseudo-inverse, we simply invert the singular values that we've already computed. This gives us a particular solution, and this we can again use to homogenize the system, right? How is this done in NGSolve? So here is now a small example code that we will use to solve the full system. Passing to this small solver sum of integrals of the DG form, a right-hand side that we want to solve for, and an embedding. Using this embedding that I've constructed already previously, we can simply build again a Trefts finite element space, an embedded Trefts finite element space. This space already incorporates all these embedding matrices, and if we set up a bilinear form over this space, it only computes the already embedded smaller DG formulation over the embedded space, which is done here. So taking the sum of integrals, using test and trial functions from my embedded space, we can construct this smaller DG matrix that you have already seen. For the right-hand side, we will have to put our forcing term, of course, our right-hand side we want to see, but we also have to subtract the particular solution. The particular solution I can get again from my embedding, asking for get particular solution and passing the right-hand side. This gives us the a grid function, or we can put this into a grid function. The grid function, of course, has to live on the full polynomial space because we are trying to incorporate local solutions that are not in the Treft space, right? So we construct this grid function on our base space, or this L2 polynomial space, solve for the particular solution, and then we need to subtract this particular solution from the right-hand side using, again, so plugging this into our DG bilinear form, AH here. Yeah? Then we can solve this DG system over the Treft space, and then we need to add back the embedding, so our final solution is made up of the Trefts, the global Trefts part, and the particular solution part, UF. And this will give us our final grid function, which is the solution of the system. Okay? Yes, with this I will pass on to Igor for our first example.
So now we have a nice method. We have applied it to the Poisson problem. We have on the unit square probably. That's what you always do with any problem. Now we will come to a more interesting problem. Let's say I have a Helmholtz equation. I want to solve that with the Trefts method. Oh, good. I have now a more complicated operator here. In polynomials, it even doesn't have a kernel. Because I'm multiplying a constant to something, the first part drops in degree by 2, and the second part just is multiplication with a constant. So I only for some eigenvalues I will be able to find maybe some functions that satisfy this at all. So now I'm thinking, what's the right method? And let us have first setup. I have a right-hand side. I have a circle, and I will say a little bit more about curving the mesh slightly later. And this is my right-hand side. I have a circle with 3 holes in it, and I'm going to solve the Helmholtz equation using the Trefts method on that. Okay, what is the correct Treft space? I take my operator here, that would be the L operator or the OP operator here. And then, as I said, I cannot not demand that it is just exactly 0. Instead, I have to formulate this in a weak sense, and I have to test with an appropriate function Q in the space pp minus 2. How do I come to the conclusion that it should be pp minus 2 and not something magical? This is, if I take the Laplacian of the space I'm working with, that's p to pp, then I get to a space pp minus 2. And if I look at one single element and I consider my differential operator, then I will know that if my Laplacian behaves as order 1, then my constants behaves as order h squared. So I know that the Laplacian dominates, so I ask the Laplacian what would be the right space for you. So even if you have a more convoluted differential equation, you have a curl operator or something like that, you should go and ask the highest order differential operator, what's the right space? And then you have some space, and you can work with that space as a good guess for the Q space. So to not say I magically know that this should be pp minus 2, I say, this must be the Laplacian of the spatial space I started with, and then I can have a look at my singular values. You remember the singular values 2 slides ago that Paul discussed, and here I see them. I have a couple of them are large, and then all of the other ones are small or very small or exactly 0. Those are the harmonic functions, because if I plug in a harmonic, say a linear or constant polynomial into here, just a 0 comes out. So for my order here, I only have 3 functions that are non-zero, and all the other ones are the harmonic functions that you saw in the nice animation that Paul discussed, so the linear ones and then one wavy one and so on. Now let's say, okay, I'm going to curve my mesh, and then something interesting happens. You can imagine some of the elements are now curved and the others are not, and if I curve my element, I do no longer truly have polynomials on my mesh element, but rather slightly deformed polynomials, and they may or may not be harmonic. They're likely not harmonic than they would be harmonic. They're slightly off linear, so here on such an element, I see a gap of 2 orders of magnitude between here, and then here I see also some things that are still positive, and I see a couple of them that are actually very close to 0. And this is for the maximal case. That's the maximum of the singular values over all the triangles I've run over to, and the minimal one, well, it still behaves as the case where I didn't curve my mesh, because most of the elements, or a lot of the elements, I will not have touched when curving the mesh. So that's something I can get out of the statistics that the Trefts embedding provides me. I can have a look, how do my singular values behave, because I maybe still need to think about what would be the right Q space. I have a good guess, but I also have to want to look by hand for the singular values. And then I can say, okay, now how do I really pick my singular values which are large and which are not large, because that determines whether I put something in my Treft space, this is 0 or this is non-zero, or do I consider them rather small, and then I have to say, this is done in the kernel, so that's the Treft space. There's 2 ways I can do this. Either I say epsilon, that's the bound for how small something is, or I can say I know exactly how many degrees of freedom I expect. That's the other variant. So there's two ways you can pass this to the Trefts embedding function. because maybe you know the dimension of this space, you don't know the dimension of the operator of the image, you have a good guess for that, and then it will just take the largest ones, or maybe you want to manually set up a cutoff for the singular values. So that being that, we can was never closed. Okay, I will close it, that's fine. Very well. Now let's compute the solution. Well, we plug this in, we have an order, and the solution looks pretty much as expected. I have the waves passing through the story. What do I use? I set up a bilinear form exactly in the same way as I would have in the GG case, because that's exactly the GG bilinear form, which I'm going to solve now on a special space on my Treff space. And then I go and call the function that Paul just discussed. It needs a right-hand side to compute the offset the particular solution to this Treff space, and then additionally to that solve a now smaller problem than I would usually have in the GG case, and this altogether gives me the solution of my Helmholtz equation. Nice, we have a Helmholtz equation now. Could do the very similar things to say, we briefly mentioned the advection reaction diffusion problem. We move to more exciting examples. We move on to the Stokes problem. We have several variables now. They will interact somehow. The Treff space is not clear which of the two should be now in the kernel of what. We are looking now basically for pairs, U and P, that together are in the kernel of my differential operator. So forget for a moment that they are two different things. We're just speaking about pairs now. We have a pair of U and P, and I have a differential operator which happens to contain two lines rather than one line of differential operator. And I'm now going to look at things in the kernel of that. So this looks like this. This is my differential operator. I need to test with something. W and Q. Here I looking at the first equation. Here I'm looking at the second equation, and I have to say, okay, this is a Laplacian. Okay, I'm dropping by 2 degrees of my polynomials here, so I'm going to test with that, and my gradient of my p happens to match this neatly. So these are the spaces I expect, and now I'm looking indeed for pairs UP that are in the kernel of this differential operator. So my finite element space, it's now no longer, so to speak, a Cartesian product of two spaces, but it used to be a Cartesian product, and now I've taken some subset of that. It's still a linear space, namely the kernel of some operator, but it no longer has the Cartesian product structure. Okay. So we're going to work with that for the Stokes case, and if you have other coupled problems, so to speak, why not? You can do the same story. Let us set up a mesh, and that's what the mesh looks like. We're having a small U-boat, and there's one peculiarity that that's good to present a feature of the Treff package as well. So we know the pressure and is mean free. If I want to have a well-posed Stokes problem, the constant in my pressure doesn't appear at all. So one way to do this is to say, I'm introducing yet a third variable, which tells me my pressure is mean free, and then I have one more unknown, and I have this standard story. Now I do not want to pass this variable to my Treff space. The Treff space is supposed to ignore this one singular unknown, and for that there exists a command ignore dovs. Ignore dovs set a bit array for what do you want to ignore. So if you carefully look at which spaces we are setting up here, and as soon as I select this, you can barely read it. I'm setting up the vector L2 space, so the G space for the velocity. I'm setting up the L2 space of an order 1 less for the pressure space, and I'm setting up one space, a one-dimensional space to set up the mean value for my pressure. Good. These are all now in here, and they are listed as in this order. So if I take the very last one, I say, okay, this one please ignore, where we're going to do trefs on everything else, and this one will just remain there in my space. It just sticks there with the space, and after that I can go along and say, okay, good. I will set up my operator now. What is my operator? I have some viscosity nu, and I have my vector Laplacian. That's still nothing magical, and that's just the Hessian and multiplied with appropriate vector component, and then taken the trace. So that's just a standard second order derivative summed up in the appropriate way. Then we have here the operator for the gradient of the pressure and my test function with that. So just a strong formulation of my differential equation. And then I have a second part, that's the second line of my differential equation, and I'm testing this with a different variable to say, also my divergence is 0, and that's now the strong local operator that I'm using to find the kernel on each of the elements. On each of these tiny tetrahedrons, you see only the faces on my submarine. Very good. After that, I call with Task Manager the Trefts embedding. What does it do? It runs in parallel over all the tetrahedrons, so it happens rather fast, and it starts to do my SVD and says, I keep that, I don't keep that, I keep that, I don't keep that. So I keep only the kernel of my operator here. So I passed my operator, and it ignores the one unknown that I have laying there around for my mean freeness of the pressure. And then I can, of course, solve this, and I can get some field lines around my submarine for the vortex forces that I put in there. So I just have a solution, much like a solution that I would expect for any other method that uses that would have this geometry on this right hand side. And what I have done is saved on unknowns and saved on computational complexity when computing this.
Okay, how quick was this? How many unknowns do you have?
Well, this is I didn't run it live. This takes a hot minute, depending on whether I'm plugged in or not plugged in. I'm not even sure this on. I have to check.
You can print the assembly.
I will run this. Spoiler. At some point, this is now run. I'm recomputing the solution now. I will get back to it when the opportunity arises.
Okay.
And then you will know an exact value.
Any sort of magnitude, that's fine.
Yeah. So too many problems, too many numbers I do not remember. I'm a mathematician. I cannot remember a single number. So.
SVD?
3, that's a high number. Next problem, parabolic problem. That's what you saw on Samantha's poster yesterday. Again, we see essentially a time stepping to do that. So what we are solving in each step is an advection diffusion reaction problem, which is scaled with dt, which comes from my time stepping, and also that I can do with a Trefts problem. So again, I have some L operator, that's my differential operator, and I'm going to use that to construct my Trefts space. the Treff space is now, and I write it down in the most abstract way. This is my L operator multiplied with my V, and I'm looking for things in the kernel of that. And now I know the other computation is now finished. So I set up some mesh and some constants in the same way I would typically do. I set up some B, and I set up the standard DG formulation to start with. And then, okay, I have my bilinear form. Have it hidden. Everybody has opened the notebook on their laptop, so they can unfold this and see the secrets. And if I now compute this, this was computed live. So you can know exactly how long it took me to compute this. And here, what do I plug in? I use my standard DT formulation to do the time steps, and I have my linear form for F, and I have my embedding that I kind of update every step. And out of that, I get my solution of my problem over here. And my finite element space is now the small finite element space that the Treff's method is giving me. So, with that would conclude my part. Before I get to Johan, I will answer your question to not leave you in anticipation. We had exactly so many end-offs in the finite element space.
And it was solved, yes.
What? And it was solved, yes.
Yeah.
By the time I had run the parabolic problem, it has already finished solving.
Okay, less than 2 minutes.
In less than 2 minutes, something like that. So there are no large condition numbers or issues.
Does it reduce in 3D? Like from what would be the full?
1 second. What would be the full? Base. Yes.
Maybe in the next one, because this one takes long.
This is fine. Yes, go ahead. I've messed something up, but
Yes.
because my mesh is wrong. No, I've reduced by nearly nothing. I've multiplied my. I've added
50,000 degrees of freedom.
Yes, that's halved here for the order that I took. What was my order? I have to. The order is probably 3. So yes, I will move on to Johan now for the conforming part of the story, and after that we can go back to more questions. The stage is yours.
Okay, thank you. Yeah, I'm here to present the latest addition to the NGSolve packet, and that is the conforming Treff's method. So it is an extension of the embedded Treff's method in the sense that we are still able to impose a Treff's condition, but we impose another restriction on the space, namely we want to find for every function in the space, we want there to exist another function from a conforming space, such that the properties of these two functions match in the sense that YH tested against all of the conforming functions in the D bilinear form is the same as the base function VH tested against all of the conforming functions in the C bilinear form. That is quite abstract, the formulation, and I'm going to fill that with life on the next slides. And for that, I'm first of all simplifying and I will look at the extreme case that the Trefts operation is just the zero operator. So in that sense, the kernel is the complete space, so we don't have any restrictions from Trefts, and can only look at conforming elements. And then, of course, the space reduces in the definition somewhat. And the basic idea how you get these conforming elements is that you assemble matrices C and D, much like you would assemble the W matrix from the Trefts operator. And you can just, you get the embedding by multiplying the pseudo-inverse of C times D, which is actually done in the same, from the same singular value decomposition, which we are already doing in the embedded Trefts procedure. So these methods fit together quite nicely. And then what I've done is I've collected several examples and compiled them into a small Python package called NGSolve, and you should just be able to pip install it if you are convinced after my talk. And now, yeah, let me run the hidden thing. Yeah, so my first and most basic example is to reconstruct a P1 element. So of course we start with a P1 base space, and the conforming P1 element has 3 DOFs on each vertex, 1 function value, and we can express that now by first of all taking a discontinuous P1 element as a base space and a continuous P1 element as the conformity space where we want to inherit the properties from. And then what we do is we formulate the C and D bilinear forms. So we have U, which is the trial function from the base space, and test against the test function from the conformity space, only on the vertices of the element. And for the D bilinear form, we do the same, except for we don't use the base space trial function, but we use the conformity space trial function. So you see these C and D bilinear forms, they are very similar in spirit, even though they technically are not the same. Yeah, and then you can just pass it into the Trefts embedding, and you get your embedded Trefts space. Ooh, that shouldn't have happened. Pressed the wrong R.
You pressed the wrong
yeah. So you of course see that I have a H1 function reconstructed. So it is kind of cyclic because we started with an H1 space and got an H1 space. So it is a silly example, but very basic. So we can move on to Crouzet-Ravia, which has still a P1 base space, but different kind of degrees of freedoms. So you can say you have evaluation at the midpoint of each edge. But actually, there's another formulation. You can think about it as an average along the facet, which is much more convenient to express in NGSolve bilinear forms. So we will use facet averages. Yeah, and you start again with a P1 space. And then as the conformity space, we choose a facet FE space. So it is polynomials on each facet, but the other facets are not coupled with the facet where the polynomial is non-zero. And then we can again just assemble the bilinear forms, but here we integrate on the boundary, not on the vertices and not on the volume, but on the boundary. And we get a a nice Crozier-Rovia basis function, which is of course also implemented in NGSolve. But we can extend the idea and move to higher order. So we take a PK space where k is of odd order, because for even order things break. And the DOFs are again evaluation at Gauss points on each edge, but let's not do evaluations of functions, but rather do integral moments. So we integrate against a facet polynomial space of one order lower. And for higher orders, you get interior DOFs. So you have moments against a k-3 order space in the interior. So you start with a discontinuous space. And now for the conformity space, you have a product space. First of all, for the facet moments, you still have a facet FE space. But then for the volume moments, you have a space defined on the volume of order k-3. You can then again assemble the bilinear forms. So here, first of all, we do the volume integral, and then we add on top of that the facet moments. And of course, because we have started with a product space, even though we add them together, the only one of the functions will be non-zero, so they do not interact with each other, but are different, and therefore we can inherit the full conformity from these spaces. And once again we can pass it to the package and run it, and get a nice basis function which is similar in spirit to the k order 1 example. Let's look at some more basis functions. So if I move it, we can see it. So here you can see it is still continuous along the facet, but also there are some discontinuities along the facets where it doesn't couple, and you will get at the very end a volume bubble. So one example which is traditionally quite hard to implement is the Argyris element, because there is no fine transformation from a reference element to the physical mesh element. But of course the Argyris element has degrees of freedoms defined, so we should just be able to define the Argyris element. Let me run that cell, which is not so important, but rather this one. It is of course a bit more complex. The DOFs of the Argyris element are first of all function evaluation at each vertex, and then you have the first order derivatives at each vertex of the elements, and also the second order derivatives. And then again you take a normal moment on the facet against a P0 space. So you get a rather big conformity space. So a P1 6 times, and then a normal facet FE space for the normal moment on the facets. But of course you can still assemble the rather big bilinear form. So you test on each vertex. So this is dx on the B boundary. You test the function values, the derivative, first order in x and y direction, in xx, xy, yy direction, and of course the normal derivative on the facets. Yeah, and then again you get a basis function. This one is of course a function value 1 here, and you can see that the derivatives and second order derivatives are 0 on this vertex. And of course we can look at more basis functions. So there are the other 3 function values of the element. Then we have first order derivative, and then yeah, some more basis function which are getting very small. So this is too small to plot here. You would have to rescale it. But here you see again the normal derivative on the facet, which is continuous. Yeah, and then of course we can go vector valued. So we can implement an HDiff conforming element, and you could do a standard BDM element, which has facet normal moments and also volume moments against a Nedelec space. But actually, if you think about it, the Nedelec moments really don't contribute to HDiff conformity. So we only really care about the facet normal moments. And we can remember that we are in a Trefts environment, so we can use the Trefts framework to fill up the polynomial space with suitable basis functions which are orthogonal to the conforming basis functions. What do I mean by that? I only define a conformity space which is a normal facet FE space corresponding to the normal moments on the facets, and I define, or I instruct the algorithm to pick basis functions which are in the kernel of the 0 operator, so any basis functions which are then orthogonal to the basis functions we've already picked for conformity. And we get a BDM space, not BDM space, but BDM-like space, where you see the first basis functions couple along one facet, and then the last 3 basis functions are volume basis functions which do not couple with other elements, but are actually Trefts basis functions. And then once we have HDiff conforming elements, we can of course think about applications, for example in Stokes. So previously we had an example where we did a pure Trefts approach for the Stokes equations, but we now want to introduce a weak sense of HDiff conformity for the elements, and still use the remaining DOFs for the embedded Trefts procedure, and we can combine that. So we have again the standard embedded Trefts setup for the test and trial space and the strong form differential operator, and we have facet normal moments against a pk-1 space. So we don't test against a full pk space on the facets, but k-1, which gives us a weaker sense of HDiff conformity. So it is non-conforming, but weakly conforming in that sense. So if I now run that cell and yeah, so we set up the space similar. One thing I want to highlight is Igor told you about the ignore DOFs feature, where you introduce a number FE space to control the mean freeness. What is also possible you can tell the test space to ignore some DOFs as unused DOFs. So what we are doing is in the L2 test space, the first DOF of the L2 space is a constant function. So we can just say, yeah, please ignore the constant functions, don't test against constant functions. And the Trefts procedure will value that decision and exclude these DOFs from the procedure. And still the conformity is only the facet moment against a pk minus 1 space. And you get these standard Stokes bilinear forms. What am I want to click somewhere else. So, and as you can see, on top I've printed the exact solution, and you get as a grid function the correct solution out of it for velocity and for pressure as well. Yeah, and that concludes my presentation. Yeah, and now I would invite questions.
How is it about like iterative solvers for these kind of methods, and can you build preconditions, or is there already some work done?
Okay, the matrix that is set up is simply a small DJ matrix, right? So the solver that you can call any solver for this, you can call many solvers.
Which one works best for large problems?
I don't know, we haven't tested it enough. I don't know, yours Bartoleschi solver, of course. It's probably the correct answer. No, yes, you can solve iteratively. We haven't played around with the preconditions.
I like the way you're using many kinds of NGSolve, how you write down the degrees of freedom to set up things and utilize a lot of core optimized components. And now my question is, are you ready for competition for certain problem classes, or is it more a proof of concept?
No, I'd be happy for a competition. Even if I lose, we can improve something.
Okay, which problem class? Where do you really think are you most competitive? Helmholtz, Stokes, Wave?
Advection. That's where we save the
Yes.
most unknowns.
Yes. A first order PDE. A first order PDE would be the strongest case probably. Yeah, like advection.
Convection problem, yeah?
Convection problem. Yeah. Yes. Because the kernel is very small. The kernel of the test. That's why the test space is even smaller for a first order operator.
So for the Poisson equation, so we lose 2 degrees when you take the Laplacian. There's only 1, so there's significantly more saving.
Yeah, I think this would be the strongest case.
There was another question at the back.
Now, so I understood that now you can use this stress strategy both for the differential operator and to impose continuity condition among the elements. But really, this really look like two opposite in the sense constraint, in the sense that, for example, if you use if you do one only saying yes and the other is saying no. But if, for example, you solve a Poisson equation with iota Lagrange finite element, then the only degrees of freedom that remains to do the Treff trick are just the bubbles, the internal one, right? Or can you do something also for the degrees of freedom on the boundary?
I didn't get the middle part, but in general you have to be very careful not to over-constrain.
Yeah, exactly.
Yeah, yes.
If you impose the continuity of the degrees of freedom on the boundary of the element, then you can do the Treff trick for the differential operator only
Yes. Then you get something similar to static condensation.
Okay.
Exactly.
And to explain why Paul was saying no and I was saying yes. So what you think of from the first part of the talk, you think we take the differential operator and we look for a kernel of the right hand side. We can also take the kind of the jump operator and we look to the kernel of that operator. And this is also an operator that the solution of our differential equation satisfies. So it's just about picking an operator for which you know what the right hand side will be. And you can either take the differential operator and then you're kind of in the first part of the talk, or you can take the jump operator and then you're in the second part of the talk.
Yeah, but for example, if you take both, how can you know that the constraints are linearly independent?
Well, you have to prove this, so to speak. You have to the test space has to be it's not for any test space that will be linear independent. You have to say for this test space it is linear independent. So the story I told with I would take the highest order differential operator, and this one will give you a clear idea. That's for the DG setting. If you're now mixing and matching with some continuity properties, just completely continuous, normal continuous, weakly normal continuous with some drop degrees, then you need to kind of be more careful with the space where you remain linearly independent.
And for the example that you want to show with the weakly imposed, the Stokes one, yes. I mean, your conditions are not linearly independent in the end. You will not have the exact reduction that you impose.
Any other questions? Okay, then thank you again. Good.
Do you want to see
No,
the?
no. I have. Or
Do you want to do this?
No. I want my.
You want more stuff? Okay. Enjoy.
You wanted to make some giving hints.
This was pre-selected.
This was set up.
Das Handy. Okay. So we have again. Donnerstag. Okay. Sieht man das? So we have again now the lunch break from 12 to 2 again, and then we'll continue with Jay talking about curvature. Yeah, I think that you still have the link for the Mensa, for example, so this still works. We would like to do now a group photo in front of the building. So please don't run away, but wait there all together that we can make a nice photo. And there is another thing. On Friday tomorrow, at the beginning, we will get first some short introduction, or some more details, let's put it that way, on WebGUI and or WebGPU and more stuff. Then we will have the coffee break. So the coffee break is now already at 10. We have moved this a little bit. And then we would have a session where there is the possibility on different choices. And for that, I would love you to click here for this Vote for Friday session, where there are now different possibilities for you to choose, depending on what you would like to do or what you would be super interested in. It's German, sorry for that. So, but one is not so much interested, at least this scale is German. And tennis, I really want to hear more about that. So please give your opinions on that. For example, you could do drafts for 10, just to make the advertisement from before. And then send here with the green button so that we can adapt accordingly.
We will have 2 sessions in parallel, right?
We will have 2 sessions in parallel, yes, exactly.
And I have one more point for this session today in the afternoon. For this web GPU and web app programming, please try to, where's the link to the Google Docs?
The link to the Google Docs is also here at the program on this user meeting material.
Link, and
So
here
here's
are some
this,
instructions to get it installed and set up.
where Matthias is modifying stuff right now.
This is very, very new technology. It does not work in all browsers, so Linux users would need to install a Google Chrome unstable or beta version.
Okay.
It sounds scarier than it is. And I think Mac OS works, as far as I know, best on Chrome and else on
that's the
Safari
file.
preview with a flag enabled. So you need to enable additional flag. So please try to pip install these packages and then try some of the demos. And if they don't work for you, just go to Matthias or me and we'll set it up so that you can also try it live.
You can leave your stuff here again in the room, by the way, if you go to the Mensa.
The voting we should do until the afternoon?
Yes,
Tomorrow,
please,
something like
until
this?
until the afternoon's coffee break. Yeah, that would be nice.
There are 2 sessions in parallel or 2 blocks after each other?
We have. We can adapt. You talked about the elastic program, right? So depending on when there are, I don't know, 4 sessions, which are everyone is super interested in. But more or less, we have 2 sessions. So 1 session with 2 in parallel. That would have been the plan.
1 session here, 1 session in the other room.
And you can choose one topic.
You can choose.
You can do whatever you like, just put numbers there, and if everyone wants to see everything, we will not be able to
Yes, exactly.
think it, but
Okay, then let's meet in front of the building for the group photo.
explain non-trivial things on curvature with easy words and Dario. Oh, good.
Oh, sorry.
Today, Ben and Peter
No, I know.
Okay, so say.
Yeah.
Stage is yours.
Yes, thank you. Thank you, Joachim. It's always a pleasure to be here in an NGSolve user meeting. Intense and entertaining, as always. Okay. So if you go to the Google Docs, you will see a link here, and if you click on the link, that should take you here. That should take you here. And there's 2 notebooks, and my plan is to go over the 2 notebooks now. One is on, both notebooks are on curvature computations. One is on extrinsic curvature computations, and the other is on intrinsic curvature computation. The extrinsic curvature, you have already seen it, believe it or not. In Enrico's talk, the Weingarten tensor came up, and we'll see that again. And in the intrinsic part, we will go into 2-dimensional Riemannian manifolds and try to compute things without really being able to visualize. But since this is NGSolve, we have to visualize. So we'll try to find a fine line there. Okay, so I have the notebooks open here. You can also get the notebooks by just clicking on this thing and going into the notebook format. Let me just make this big and see if we need to do some computations. The notebooks are open, but maybe I'll just try to explain. Not sure if this is big enough. Can you all read? Anyway, so I hope you can read. So curvature is an important topic, not just in geometry, but in areas like shells, which also came up multiple times actually in this workshop, and will come up again in Eduardo's talk. It's because it's important in numerical relativity. It's also important in computer graphics and so forth. So the agenda for this notebook is to show some techniques in NGSolve that allows you to compute curvatures of 2-dimensional surfaces. Okay, so we'll start with embedded smooth surfaces, meaning that it's a surface in the sense we know. It's a 2-dimensional manifold that's sitting inside R3. So we have all the facilities of R3. We know that in Euclidean domains like R3, we can differentiate in X, Y, and Z directions. Okay, but now when we, the intuitive notion of curvature is quantified using the normal vector of a surface. If you look at a surface and you want to know how it curves, you look at the normal vector of the surface and see how it moves. If the normal vector is not moving, the surface is flat. If the normal vector is moving, by looking at its derivative, you can quantify curvature. So this normal vector is a vector field on a surface. So in order to know how it changes, in order to compute the derivative of the normal vector, to know how it changes, we need to know how to differentiate things on a surface. So here is an elementary definition of differentiating things on a surface. You merely take a function on a surface, extend it in a tubular neighborhood of the surface, and then use the usual differentiation. And then you project onto the surface. You project onto the tangent plane of the surface. This is the tangential projection. Nu is the normal vector to the surface. This is the tangential projection. And if you take the usual gradient, this is the usual dx, dy, dz gradient, and you take its projection, you get the tangential gradient of a scalar field. If you do that component by component, you get you can apply the same operator, tangential gradient operator, to a vector field. The surface gradient of a vector field is exactly this object.
if you take the surface gradient of the normal vector, you are beginning to see curvature. The surface gradient of the normal vector describes how the normal vector is changing, and that should be a very intuitive notion of curvature. That thing is called the Weingarten tensor. So here is W, it's a 3x3 matrix field obtained as a surface gradient of the normal vector. This is an object you see in the first course in differential geometry. A lot of things are known about it. First, W is a symmetric matrix field. Second, W always has the normal vector itself as an eigenvalue, as an eigenvector corresponding to 0 as the eigenvalue. So you apply this thing to the normal vector, you will get 0, and that just comes out of the property that the normal vector is a unit normal vector. It has constant length. So it's a symmetric matrix, so it's a 3x3 symmetric matrix. It's got 3 eigenvalues. One of the eigenvalues is 0. There are 2 other eigenvalues that are remaining. Those are called the principal curvatures. They are K1 and K2. If you take its product, you get the Gauss curvature of the surface. If you take its average, you get the mean curvature. Okay, so these are the fundamental curvature quantities, K1, K2, K, and H. And all of these can be easily computed sitting inside NGSolve. So let's begin with the simplest case, the case of a sphere. Sphere, at any point on the sphere is curving equally in all directions, so we expect both the principal curvatures to be the same, and we expect that nothing will change from one point to the other, and all these expectations are confirmed by analytical hand computations, and you know that the principal curvatures are going to be 1 over the radius. Gauss curvature is going to be the product of the 2 principal curvatures, so it's 1 over r squared, and the mean curvature is the average of the 2 equal quantities. So all of this is known. Okay, so let's verify that this comes out of a simple computation in NGSolve. We make a mesh of the sphere. This is done by meshing, by stopping the meshing process before it does a volume meshing. So we say somewhere here that you perform a meshing, and the last step is just a surface meshing. So this is a hollow sphere. And the Weingarten tensor, the computation of the Weingarten tensor is just this one line. You take the normal vector nu, you obtain it using a ready-made special coefficient function, and you just say grad of nu. Grad is performing the surface gradient. Okay. And you end up with this 3x3 matrix, and then you can do things with that 3x3 matrix. You can take the trace of that 3x3 matrix. The trace is the sum of the eigenvalues, and we talked about this matrix having 3 eigenvalues, 0, K1, and K2. So if I want the mean curvature, all I need to do is to take the trace and multiply by 1/2. So that is the mean curvature of a sphere. And you can see that this is a sphere of radius 1, I think. 2. Okay, I did 2, right? I hope I did 2. Yeah, okay. Okay, good. Thank you. So its curvature is 1 over 2, that's 1/2, and you see it's pretty much 1/2. There are some numerical errors that appear like stars near the vertices, but that's just because the curving is not perfect. So it's not a completely smooth manifold, right? It's smooth up to the representation of the geometry on the computer. And you can, if you don't trust me on that, you can change this curving order, which is somewhere over here. You see here we're saying that the mesh should be curved up to some curving order, and I think the curving order is set to 3. And I'm sure that if you take the notebook and compute it with 5, the stars will look like something else. The error will disappear. Okay, so all right, so we know how to compute the mean curvature. How do we compute the Gauss curvature? It's a product of the 2 principal curvatures. So if I had the restriction of the Weingarten tensor, to just the tangential part, then I could take the determinant of that. Okay, but we can do that with some cofactor matrix magic. Another way to do it is take the Weingarten tensor and where it has a 0 eigenvalue, change the eigenvalue to 1. So it had a 0 eigenvalue with the normal vector as the corresponding eigenvector. Now if you add this rank 1 term, then this matrix will have the same eigenvalues as before, except the 0 eigenvalue has become 1, and now you can take the product. And the product of the eigenvalues is the determinant. So all we need to do to compute the Gauss curvature is the determinant of the Weingarten tensor to which a rank 1 matrix is added. And you can see that the Gauss curvature is coming out to be about pretty much a quarter and something, an approximation to a quarter. Should be what we should see. Okay, so nothing special about the sphere. We could do this to any surface. So I have just written a few lines encapsulating what we just did into a function which we can repeatedly use on other surfaces. All we do is to take grad of nu and then compute the mean curvature, the Gauss curvature, and the principal curvatures. Oh, I forgot to say, so if I wanted to get the principal curvatures, and I know that this is the product of the principal curvatures and this is half the sum, I can solve a quadratic equation from high school and we will get K1 and K2. Alternatively, I can solve an eigenvalue problem. This is also possible, and I wanted to do that because I wanted to show eigenvectors, but then the facility to plot things, vector fields on a surface was absent until the next hour or so, I think. And then maybe things will change. So, okay, so you can certainly solve an eigenvalue problem, and then you get the principal directions and the principal curvatures. Okay, here's the second example: cylinder. A cylinder is interesting. It's curved in one direction. So you would think that there's no curving in this direction, so the principal curvature in this direction should be 0, and the principal curvature along this direction, that's just like the curvature of a circular curve, so that should be 1 over the radius. So that should be the two principal curvatures, and we can verify that that is what we will get either analytically or by computation. When you compute, you see the did that go away? I don't know why I did that. Okay, so here are the two principal curvatures. One appears to be 1/2, as we expect, and the other one appears to be 0. Right, so this is the 1/2 and the 0. And if I take the product of these two, I get the Gaussian curvature, and the Gaussian curvature should be 0. So the cylinder has the interesting property that although it looks curved, it's got 0 Gauss curvature, and it's got a non-zero mean curvature. Now, why does it have 0 Gauss curvature? Well, this is related to Gauss curvature being intrinsic, because you can cut the cylinder and lay it down as a flat piece of paper without. So it's curvature, the curvature of the flat piece of paper, and that of a cylinder must be the same. Here is another example, an example of something called a pseudosphere. A sphere has constant Gauss curvature, but positive Gauss curvature. A surface of constant negative Gauss curvature looks like this, like a horn. That's called a pseudosphere, and you compute. You apply the same routine. You compute the Gauss curvature, and you find it's -1. And the principal curvatures have opposite signs now. One of the principal curvatures is positive, and the other one is negative. Okay, so these are examples of extrinsic curvature computations on smooth embedded surfaces. Now, when we go to a non-smooth surface, this notion of how does the normal change, we have to adjust our thinking. The curvature amounts to quantifying how the normal changes. So we took the derivative of the normal. Now, if I have a kink and the normal here jumps to another normal here, then we expect a source of curvature along the edge, and this is perhaps related to how the normal changed. So one way to quantify that is to look at the angle by which the normal changed and put that as a distributional delta on that edge. Okay, so that's a guess, and now you can establish it, and so on and so forth. So here's the angle. On an edge, if I have an edge that is shared by two elements, t plus and t minus, then there is a normal on t plus and there's a normal on t minus. You look at the angle between them. That is like a jump, the jump of the normal. So in addition to the usual Weingarten tensor on individual triangles, if I add this sort of a distributional term on the edges, then I get a generalized Weingarten tensor. This is written as a functional in this formula. It's a functional that's acting on this. This is a generalization of a symmetric matrix field, and we're generalizing it as a functional acting on other symmetric matrix fields. And then we can ask what is the right space for sigma and so on, and we could have a long philosophical discussion about it, but I'll just say that the sigma ought to be the Helen-Hermann-Johnson space on the surface. The reason essentially being that this quantity needs to be single valued across the element interfaces. So when you take the Frobenius inner product of mu is a conormal vector, nu is a normal vector, t is a tangent vector, and then what is remaining is the conormal vector. So when two facets come together and you have two different conormals, and you want this thing to be continuous, or this thing to be continuous across, even when sigma is not continuous and mu is not continuous, the right space for that is the HHJ Flaner-Doman space on a surface. So we can define the Weingarten tensor as a functional on the Helen-Hermann-Johnson Flaner-Doman space. But now this is a functional. This is like a distribution, and you can't see it. I mean, it's so. But we won't see it. So what do? So what we do is we take this functional and make it look like a function by a Riesz representation, or by solving a mass matrix. We put the function on the right hand side, and we say, well, we can't see this, but we can see what is the representation of that functional as a function in the same Hermann-Johnson Flaner-Doman space. And we have some pictures of this lifted representation of this distributional functional. Okay, and the code is this. This is where you see the element contributions from the smooth part. Each element is smooth, so this is well defined within an element, and this is where the distributional part is added as element boundary terms. And here are some examples. This is a nice smooth ellipsoid surface. Suppose we destroy the nice smooth surface and approximate it with piecewise flat surface. Okay. If we approximate this by a piecewise flat surface, then if we try to compute the curvature by looking at the curvatures or the Weingarten tensor inside each element, this is flat, so it's got no curvature, so the Weingarten tensor is 0. So all the element contributions are 0. So in fact, the entire curvature when you do this approximation resides on the edges. So those edge contributions are the ones that will give you the right curvature, and so if you don't add that, then your curvature approximations will be completely useless on these flat, piecewise flat approximations. So I've just shown you the implementation of this this formula, and then we do this curvature functional, we lift it, and it begins to look like the exact mean curvature you saw here, more or less. It just it's like a piecewise constant approximation to the exact piecewise to the exact smooth, and this approximation improves as your mesh size becomes finer and finer. No, but these jagged lines will disappear eventually. Okay, so that's the extrinsic curvature computation. And now I will go into the next topic, which is intrinsic curvature computation. Okay, and why intrinsic is a reasonable question. Why do we worry about doing intrinsic computations? This is about not using the embedding information of how the surface is embedded inside another surface. In other words, if there is a being which lives inside the surface and cannot possibly know anything outside of the surface, how would that being compute the curvature of the surface? Is that even possible? I mean, you would think, I would have thought before knowing all this, that this is not possible, that if I'm a two-dimensional being sitting inside a surface, I wouldn't know how the surface is curving. And you have to appreciate the genius of Gauss, who I don't know how he saw it, but he saw that through calculations that it is possible to know how a surface is curving, sitting inside the surface. And we're talking about these beings as if they're alien beings, but this is, we're talking about ourselves, because we are sitting inside a four-dimensional manifold and we don't know if we're embedded somewhere else. But we still can compute the curvature when we routinely compute the curvature of the space-time that we live in, because without that your GPS will not work on your phone. You need the relativistic corrections to be able to precisely locate where you are. So now we take this for granted, but this is still, it's at least for me, it's still kind of mind-boggling how it's possible that, okay, it's just, you'll see that it's just formulas, it's just mathematics, and then we get over the surprise. Okay, so here is what you saw in the previous extrinsic approach. In the extrinsic approach, there is a normal vector to the surface. Then, even just to talk about the normal vector, it's pointing outside of the surface. You need to know where it's embedded. So that's not intrinsic. You have to get out of the surface for this approach. Then there is no meaning to nu in the intrinsic approach. Okay. So just to start with some example, here's a hemisphere. Okay, a hemisphere has the same curvature as a sphere, so we've seen that before. But I'm just making a hemisphere, and I'm plotting. Well, this time its radius is not 2, is 1. Right? Okay, so and then we see the curvature, Gauss curvature is 1, as expected. In the intrinsic approach, we're not going to be using the Weingarten tensor. We're not going to be using the nu or the w. So what are we using? We're using the metric. The metric on a surface is a 2x2 matrix field that we can use to measure angles on the surface and lengths on the surface. Okay, so if you have an embedded surface, then you can extract a metric. But you can also have a metric that is just God-given and doesn't come from an embedding. Okay, so, but because we want to see some pictures, let's look at this hemisphere, which is an embedded surface, and let's compute its metric. In fact, for any embedded surface, you can compute a metric. If theta is the embedding, all you have to do is to take the gradient of theta, transpose, multiplied by gradient. This is very familiar to those of you who have worked in elasticity. the gradient of theta is theta being the parameterization is a 3 by 2 matrix. So this thing after you've multiplied these two matrices becomes a 2 by 2 matrix. Okay, so here is the hemisphere example again. Except now I don't see the hemisphere, I see just a parameter domain. So this is like the shadow of the hemisphere. On the bottom you have a disk, that's the parameter domain, and then you make a mapping theta that makes this parameter domain look like the hemisphere. And the parameter domain is just a parameterization obtained by spherical coordinates. So you can sort of identify the spherical coordinate expressions here. And once you have that, you use the deformation capability of NGSolve to deform the mesh. This is the parameter domain mesh. Parameter domain mesh is param underscore mesh, and then you deform it using the mapping we just wrote down here, and then you get a hemisphere. Okay, so we have the embedding, and once we have the embedding, we compute the metric using this. That's done here. This is the deformation gradient, the gradient of the parameterization. F transpose F is doing exactly this, and that is our metric. That's the metric on the surface. Okay, so in order to get the metric, we use the embedding information, and now we're going to forget the embedding information, because the rest of the computation should only use the metric. Okay, and the idea being that if the metric is coming from somewhere else without an embedding, we should still be able to do all the same computations. You can this matrix G is interpolated into something called the Regge finite element space, which maybe you would explain. Oh yeah, right? Yeah. Okay, so maybe I don't need to explain that. So here is the magic of Gauss, which you know is a set of formulas. I don't know how to make these formulas any easier than they've been around for hundreds of years, and you can still stare at them. He says that the Gauss curvature is equal to this quantity over the determinant G, and that this quantity is equal to this with all the Christoffel symbols, and the Christoffel symbols are derivatives of the metric. Super clear. Okay, so if you can compute all of these derivatives, you can compute the Gauss curvature just from the metric. All right. Okay, so we could implement these formulas in Python by doing the differentiation of coefficient functions with the facilities in NGSolve, but in fact NGSolve has already implemented this, and you can get this tensor. This tensor is called the Riemann tensor, and you can get all components of the Riemann tensor, which is implemented in C++. So it's faster than writing this in Python. So I was initially writing out these derivatives in Python, and then I gave up very quickly, and just it's not worth it. All you need is this line. You take the grid function, which represents the metric, and apply the Riemann operator to it, and then you get the Riemann tensor. And you take in 2 dimensions. It turns out that the Riemann tensor has only one independent component, so you don't have to read too much into the 0, 1, 1, 0. All other components are going to be plus or minus that one component. Not so in higher dimensions, but knowing that is like knowing the curvature. And this is the formula. This is the formula of Gauss, and you get exactly the same number that we saw from the extrinsic computations, 1, because this is radius. This is radius 1, but we have never left the parameter domain. We don't know anything about the embedding. We just the parameter domain came with the metric, and we just differentiated that and applied the formulas. So this is an example of the intrinsic computations. Now to get a feeling for how to extend this to non-smooth intrinsic manifold intrinsic computations on non-smooth manifolds. There is another theorem that's useful, another theorem from geometry called the Gauss-Bonnet theorem, and it's also a remarkable theorem because it ties to two areas that are apparently distinct, geometry and topology. It says that the geometrical quantities add up to a topological quantity. Namely, if you look at the Gauss curvature and you integrate it, you get the total curvature of the manifold. That plus this quantity, which I have to explain, is called, if a surface has a boundary, then the boundary curves have something called a geodesic curvature. That's this quantity. And then if the boundary has vertices, then the vertices form a source of curvature, and the angle there, you add them up along all the vertices. All these curvature quantities add up to a topological quantity, 2 pi times the Euler characteristic of the surface. Okay, so what is the Euler characteristic and what is the geodesic curvature? So let me quickly explain that. It's possible to explain the geodesic curvature intrinsically, and that's what we will do the computations that we'll do would be intrinsic. But it's much easier to understand what geodesic curvature is extrinsically. So if you have a surface and you want to know, and you have a curve on a surface, and you want to know what is the geodesic curvature of that curve on a surface, you pretend to be a bird perched on top of the normal vector of the surface. Right? So here's the normal, and I'm the bird looking down, and I see the curve as if it's a planar curve. And planar curves, curvature of planar curves are easy to understand. You just try to fit a circle and measure the radius of the circle. One over that is a curvature. So geodesic curvature is what the bird sees as a curvature of this curve. Okay, so for example, if I'm on a sphere and I draw a great circle, I perch myself like a bird on top, and the great circle looks like a line. So the great circles have 0 geodesic curvature. But if I'm higher up, in one of the higher up latitudes, then I perch myself up and look at it, it looks like it's curving. There are higher latitudes would have some curvature, some geodesic curvature, whereas the great circles will not. Here is the intrinsic definition of geodesic curvature, which is harder to explain, but this is what we'll use for computation. You're taking the tangent vector of the curve, and then you're differentiating it along the tangent direction and looking at its normal component. Okay, nice short formula, but deeper. Okay, so this object here can be computed in NGSolve using a special coefficient function. And this is how we're going to compute the geodesic curvature. The Euler characteristic is a topological quantity, which is kind of, I guess, easy to explain. If you have a closed surface, if it doesn't have if it has gamma number of holes, then the Euler characteristic is 2 minus 2 gamma. So if I have a sphere, it doesn't have any hole, the Euler characteristic is 2. If I have a surface of a donut, a torus, it's got 1 hole, so it's got 2 minus 2, and so on. You could also compute the Euler characteristic by counting the number of facets, the number of edges, and the number of vertices. This is like a ready-made formula before finite elements, so it is super easy for us to compute the Euler characteristics. Okay, so typical examples. This is Euler characteristic 2. This has Euler characteristic 1, and this is Euler characteristic 1. And you can apply the Gauss-Bonnet formula to each of them and realize that it is true. I think maybe I don't want to take too much time away from you, so I will skip some of this. Let's just go back to the hemisphere example we saw. In the hemisphere example, we have one boundary, which is a great circle, and I just got done telling you that the great circle has 0 geodesic curvature. So there's no contribution from the geodesic curvature. There's contribution from the Gauss curvature on the surface, So one side of the Gauss-Bonnet, there are no vertices, so one side of the Gauss-Bonnet formula looks like this, and on the other side is 2 pi times 1. And we could verify if whatever we are computing satisfies this. So here is a verification using the extrinsic approach, and we integrate, and we'll see that both the integrals come out to be equal to 2 pi. In the extrinsic approach or in the intrinsic approach using the Riemann curvature, you get almost 2 pi. So up to numerical approximations, you're satisfying the Gauss-Bonnet formula for the approximations you generate. Okay, now comes the confusing part. Take the cylinder we looked at earlier and cover it up on the ends. Now you have a cylindrical box instead of a cylindrical surface. Okay. What should be the Gauss curvature of this object? We know the Gauss curvature here is 0 because it's not curving in one direction. We know the Gauss curvature on the flat ends must be 0. Okay, so if we compute the Gauss curvature using any of the approaches, the intrinsic or extrinsic, we're going to get 0. Okay, but the Gauss-Bonnet formula says for closed surfaces, we should have formula like this. This is equal to 2 pi times 2, 4, because Euler characteristic of closed surfaces is 2. So this should add up to, this integral should be 4 pi. Instead we're getting this integral to be 0. Okay. Of course we're not contradicting Gauss-Bonnet theorem, because Gauss-Bonnet theorem was only for smooth surfaces. What is happening is, however, requires some thought about what's going on this non-smooth edge. Okay. If I smooth the non-smooth edge, then of course the Gauss-Bonnet theorem applies. So my integral is no longer 0. The integral that 0 integral you saw before suddenly becomes 4 pi, and I can make this thing as small as I want, as long as it's curved. Maybe I have to I curve it sharper and sharper. It'll still be 4 pi. So how is it possible that you got 4 pi here and then the moment you make it look like this, you got 0? So there's something missing there, right? Okay, so that's our first indication that there is a source of intrinsic curvature on that edge, on every non-smooth edge. And if you look at how the curvature looks like for the smooth edges, it's pretty much 0 everywhere except in this edge, in this rounded off part. So this is going to become larger and larger as your curvature on that edge increases. But the purpose of this example is to show you that there is an edge delta-like distribution on those that acts as a source of curvature. And we could even argue a little bit more and see what form should the delta take. Well, it's the curvature is 0 here. Let me go back to this picture. On this picture, the Gauss-Bonnet theorem applies to the smooth parts. So it applies to this part and to this part separately. So you can apply the Gauss-Bonnet theorem here and say, oh, okay, the integral of the curvature here and the geodesic curvature on this edge should add up to 2 pi times chi. And similarly here, if I look at this curve as a boundary of this surface, I would perch myself on top of this normal vector and look at this curve, and I see that the geodesic curvature is 0. So there's no geodesic curvature from this surface, but if I look at it from here, I do have a geodesic curvature, and the geodesic curvature is related to the radius of this curve. So you can actually argue that the edge delta distribution must be the jump of the geodesic curvature across that edge, just to satisfy the Gauss-Bonnet theorem. So that's our first suspicion, that what we should add in order to get a reasonable definition. Okay, but that's not all. Here is another example that clarifies things further. If I look at a cube and then round off the edges, I see nothing here on these edges because these edges are geodesic edges which are not sources of curvature. All the curvature is concentrated on the corners. So there are vertex contributions in the limit. And what should the vertex contributions be? That turns out to be a classical object called the angle deficit. How do we see this? Put the cube like this and look at this vertex. At this vertex, I can measure the angles. There are 3 angles here: this angle, and this angle. All of these angles are right angles. So if I sum up those right angles, I have 3 times 90 degrees. I do not get 2 pi. If I'm on a flat surface, and if I had three vertices coming together, the angles would add up to 2 pi. Here, I don't get 2 pi, and that is a sign that something is protruding. There is a sign of curvature. At the deficit in the angle, the sum of the angles do not add up to 2 pi, but something less. That deficit is a classical object studied by Tullio Reggi. And here's the definition: 2 pi minus the sum of the angle, the deficit in the angles. On this flat diagram, of course, I'm going to get 2 pi, but if this were the top of a hill, and I measure the angles, and I don't get 2 pi, and that difference is this theta v. That is another source of curvature. You add them up all together, you will get a generalized Gauss curvature for non-smooth manifolds. Here is the angle deficit contribution. Here's the contribution, classical Gauss curvature contribution from smooth elements. Here's the geodesic contribution. And I've motivated all of these from using the previous examples, and the rest is implementing this and visualizing this. And I think I'm kind of out of time, so I'm just going to show you a picture of a nice smooth looking curvature that is approximated by a piecewise flat metric, and the curvature approximation comes out good, and you can prove that it converges and so forth. And I'll just put up the references to the works where these formulas are studied and convergence is proven. And thank you.
Jay, taking the fear away of the Riemann curvature operators. Any questions?
So what can you say? I mean, you reference to the papers, I should probably read them, but what can you say about the accuracy that you get from these implementation approaches?
Yeah, so you could prove that this if you start with a smooth manifold and you're having a non-smooth approximation to a smooth manifold, then the curvature that you compute converges to the original smooth curvature with order h to the k, where k is the degree of the in a negative norm. Sorry. Yeah, curvature is like a second order operator. So if your metric is approximated to order k, you expect to lose 2 orders. But then we prove that we don't lose that much, and it's a whole story about the convergence orders. But it does converge, and I mean before we started, I think Gaulik started this business, and before Gaulik, I think the only work that was tackling these kind of things was in the geometry community by Chigger, Miller, and Shader. These are pure math people. They proved that this angle deficit converges in the sense of measures. That was the best result at that point. But now, I think thanks to numerical analysis tools, we can say much more.
Besides the conversions, is some balance exact? Is sum up the distributed curvature? Do you get the exact?
Right. I mean, we made it up so that this lifted curvature satisfies the Gauss-Bonnet. So
the integral is exact.
Yeah.
Can one use this curvature to in some way resurrect continuous normal field, rather than if I have some corners and the normal field, the one I get immediately is the one that's discontinuous,
So here in, I mean,
Normal field that is continuous?
you saw that we can directly curve the surfaces, but you're saying you don't want to directly. This was supposed to be a cube, and we rounded the edges.
Sure.
So we could do that, but if you don't want that, you could take the Weingarten tensor, the distributional version of it, and when you lift it up, it smears out. So you would have the derivative of the normal, the lifted version of the derivative of the normal that is smoother than the original, and then from that perhaps you could reconstruct a smoother normal.
Okay, very good.
But and if the manifold is not smooth, which kind of convergence can improve?
If manifold is not smooth?
Yes.
We don't have a theorem.
Okay. Because also the representative that you use for the plot, you will see that it explodes, right?
Yes.
Because then you cannot represent a direct function.
Yeah. So. Okay. There's a question. Okay, if you have a non-smooth manifold, then what should be the right notion of curvature? And our approach to answering it is, well, if it were smooth and if you made a non-smooth approximation, then what we are proposing will converge.
Okay.
But if you have some other criteria to judge that you got the right thing for a non-smooth manifold, let me know, and I'm sure that ours will satisfy it. I don't know.
Okay, sounds interesting, and if you are interested, but let's shift it for later or tomorrow, and continue with next talk by Eduardo Bonetti. By the way, doing some.
Okay.
Yeah.
So, thank you for the introduction. There was a little bit of a lie in the sense that today I do not do curvature, but many of the things that are explained in the curvature you can maybe relate it to the talk. Okay, so today we solve a non-standard eigenvalue problem using or trying to find the preconditioning somehow. All the things that we are using are can be found at some point in a joint work between Joachim, Jay, and Kaibo. And with Joachim and Jay and Kaibo, we try to go from the analysis basically or the continuous spaces to the discrete spaces. But let's start with this non-standard problem. What you see here is very similar to something known as the Maxwell equations. Okay. And sorry, can you? Okay, they would be Maxwell equations, easy to treat, or we know a lot about them, but what about if we now substitute E and B with some matrix field? And what about if this matrix field are, for example, symmetric, traceless, and divergence-free? Then it starts to be a little bit more of a complicated problem, right? Okay, and now what we do, we basically decouple the problem using some gamma is equal to E or B, and we can arrive to a very standard form for an eigenvalue problem, still with the same conditions of symmetry, etc. There are many ways to solve this problem. One way could be, for example, to find again using a mixed formulation. This mixed formulation leads to something known as a G-type eigenvalue problem, or type 2 eigenvalue problem. And now the question is, in what kind of space do we pick this kind of functions or finite elements? Okay, the sequence that you see here is the Deram sequence. Here is the notions. Not useful. Why not useful? Well, if we pick H1, we need to find, we need to create a tensor product of H1 9 times, and then maybe you can apply some symmetries, but you need to implement, to penalize the problem too much, okay? The same thing could be for H curl and for H div. L2, we'll not even talk about it. But what about maybe extending this sequence onto more interesting sequences? So the first sequence is in a Sobolev space, a positive order Sobolev space. The second sequence you start to be distributional, okay? Not anymore weak, but distributional. So all the things that you see here now are in H-1, okay? The dual space of H1, 0. And now the game is let's try to fill up the innermost part of this square, okay, this frame. The first thing that we do is the following. So we pick one very easy differential operator that is the Hessian, okay? And obviously the Hessian is going to be what? Is going to be the gradient and then the symmetric gradient. The first space that we have is H curl, so needs to be something that commutes, let's say, somehow. And the definition of the space is going to be something that is in H minus 1. It's symmetric. The curl is going to be in H minus 1, and the inc operator is in H minus 1. So the curl operator is the operator row-wise, and the inc operator is the composition of the operator, the curl operator row-wise, and then the operator column-wise. Okay, that's complicated things. We can play this game for the rest of the space, and here it is, the full space. So we call the first one H curl curl. Usually H curl curl is the space in which you see the metric for a Riemannian manifold. H curl div is very similar, so the divergence is in H minus 1, the symmetric curl is in H minus 1, the curl div and then div curl is going to be in H minus 1. Okay. In particular, if something is defined on this horizontal line, is going to act in row-wise, it's in the vertical lines is going to be act column-wise. Okay. But what we see basically is that we finally have something like a sequence that could be helpful, okay, to discretize our problem. And in particular, in this sequence, you have some properties like exactness, and so that's the way to go. And now we come back to a topic that you explained in the previous part, or more or less. It's that we need to go distributional. Why? We are not in L2 anymore. We are not definitely not in H1. We are in H minus 1. So if we start with something that is, point out, something like a Lagrangian element here, we would love to have something that lives here. Okay. So if we start with something that is a Lagrangian of a finite element, sorry, of something that has order p is equal to 1, we would love to have something that has still some values in the next space. Okay. Here I do the formal the derivation, so you can follow a little bit better. So the derivative or the Hessian of something, we apply the definition of the distribution. So we get the formula joint, integrate by part on a mesh, use the fact that Vn is continuous, integrate by part again, and then through continuity of this small object here, we arrived at a formulation that we like. And now the thing is, from this formula here, you somehow can guess what is the correct space that we obtain after the Lagrangian, when we apply the Hessian on the Lagrangian. And this is going to be the Regge space, okay? So the space that has degrees of freedom, has the length of each simplex, okay? Plus something more. And this something more is actually something distributive, okay? So this is going to be the normal value of the gradient of V, and then normal with respect to a face, and then that's it. By the way, the same thing could be done for the other spaces. Definitely, I don't have time to talk about it here. One thing that I want to point out, if you apply a distributional differential operator to something that lives on a simplex, then you have, as a result, something that lives inside the simplex plus something on the face. If you do the same thing on the face, you obtain something on the face plus something on the edge. And here, for example, for the curl, you obtain 4 terms, okay? And these 4 terms, the first 2 basically come from the volume part, and the second 2 come from the face part. The problem is that in this new kind of sequence of discrete spaces, we don't like to work on the edges. So having a finite element on the edge is really, really bad. Don't. If you want to implement one, have fun, but not so fun. So somehow we need to kill these really bad terms, curls on the edges. And here is the problem, okay? So the problem is we know how to, so the above here is the problem, and we need to work in a space in which somehow we can visualize, let's say, the result. So the first part is an inner product, L2 classical inner product. The second part is a duality pairing. So we need to find this duality pairing. And this thing here is a duality pairing, okay, between functions that are in H minus 1. Okay, so the representation of the rightmost part, okay, this inner product, this duality pairing here is the following. So you go from H curl curl to the dual of H curl curl, that we are lucky is H div. We compute a representative using the mass inverse, and then we go back basically, okay? On the right hand on the left hand side, sorry, A is going to be basically, you bring everything in a matrix form, and then you easily can get that it's exactly this thing here on the left. A is great, it's symmetric, positive, semi-definite. It knows, so we know the kernel is quite big, it's the Hessians, but we know it. It's possibly not so sparse, because we need, if we take the actual inverse, it could be really bad, okay? So we need somehow to stabilize this problem, or penalize this problem. The things that we need to penalize are, well, I will show it later, but the strategy to penalize everything is, to, instead of using a mass inverse as we did for the previous term, okay, so you see that the previous term we have mass inverse and mass inverse, we use something that is spectrally equivalent to the mass inverse. And that's it. That's really, this is what we have to show then with NGSolve. And now the problem AK, okay, we have this matrix to, we need to find the preconditioner for this matrix AK. AK is something that is dense. It's not so nice. Not properly dense, but I'll show you later what I mean. And then something that you can work with, something that is a little bit better. So the idea now is that instead of using the actual mass inverse, we use still something that is spectral equivalent, and we use a precondition for the curl div space. And that's it. From this A tilde, or A hat, sorry, we can extract a preconditioner, and then we can solve the problem maybe using something like log-BCG or your favorite eigenvalue solver. Now, what should we observe from as a result? Well, usually the problem that we solve is similar to something like a Laplacian problem, okay? And the Laplacian problem in each entry. And now we have 9 entry. By symmetry, we can reduce it to 6 entries. And again, by tracelessness, we can reduce it to 5 entries. So we should observe 5 things. This is for later, but really, okay. And this is maybe a little bit the only theory that I show you today. There is a theorem that tells you that if you have something that lives in H curl curl, then you can decompose this thing into smoother things. So you find something like gamma tilde that is smooth, H1, and then you have a vector that is still smooth, and then you have something that is again smooth. And now the problem is, okay, if we know what's the trace and the trace lives in L2, then the trace, if the trace lives in L2, then the whole matrix lives in L2. And that's great, because now we can, if the trace is 0, this lives in L2, and then we can visualize the result, okay? So it makes sense to visualize the result, and this is the theorem. Okay, let's show you some code. How much time do you have? Not much. I will be quick. Okay, this is the problem. This is, can you see it? Yeah. This is the problem. This is the matrix that we need to implement. And okay, we import our add-on. Easy, very nice tool. We create this mesh. Okay, not so big, but okay, just to visualize something. We create the new space. As I said, the space is going to be H curl curl and then something else. So we need to armor the space with something of polynomial order higher. One more. Okay. Okay, P2, that's fine. We have a lot of degrees of freedom already. So be careful. Again, we need when we apply the curl, we get to H curl div dual, and then we need to take the dual that fortunately is still H curl div, or a little bit like this. How much time do we have? Not much, right?
15 minutes.
Oh, I'll try to be fast then. Okay, anyway, this is the formula for the curl. You can take a pen and paper and derive it. Here we have two matrices. One matrix is to project it into a normal space, the normal part. The other one is to rotate it against the normal. And thanks to, I think Michi was the one that implemented it. I don't know, I can't remember. Anyway, we have the Einstein summation that comes in quite handy. I highly suggest to use it. We can create this kind of matrices with a no? Is it a no? No, okay. Okay. Something that I want, oh yeah, that's it. Yeah, let's just run it and okay, you can spy the matrix. The matrix is going to be, well, sparse with a lot of zeros. Here I wrote the number of non-zero elements versus the number of total zeros. Let's the total entries, sorry, and then the number of zeros. So we could get rid of the zeros every time. I'm not going to do that. I recommend to do it when you can. Again, like matrix inverse, and here is the game of taking an operator matrix and then taking a mass matrix, inverting the matrix, and compose them. Okay, and here the matrix A, and here before I said that you cannot sparsify it. In particular, you can, if you try to get the sparse matrix of it, it tells you, no, you can't, because you use something that is the sparse Cholesky. Okay, so this could be something that you can need to take care of. Okay, we play the same game with the mass matrix. The inverse the dual space of the Reggie space is the TD and an S. Okay, polynomial order one more. Okay, oopsie. Okay, we get the mixed part. So the mixed part is the, let's say, one thing that maybe I should explain here. This is an inner product. I don't know, do you like the inner product written this way, or do you prefer inner product? Let me know, let me know. Okay, and this is just a pairing of the face part and the volume part, okay. Okay, well, again, the lifting, we define the matrix M, and now it comes the part of the penalizers. So the penalizers, we need to play the same game. So define the operator, going to a certain space, invert the mass matrix that it should not be the exact mass matrix, so it needs to be something approximate, and then go back. And this is exactly what we're going to do. So define the trace, for example. I'm not going to spy all matrices because this is too long, but take only the diagonal inverse, so not the whole inverse, okay? Spectrally equivalent, or more or less. And here we can extract the sparsification of the matrix, okay? This is important. Okay, and we do the same thing for the bad curls. Now the bad curls are really bad in the sense that whatever space you use to be in the dual space or to pair it with, it's difficult to treat. The idea is the following: you only need something that lives on the edges. So you cannot use, for example, H curl because it's orthogonal to this space. You cannot use HDiff because it's normal to the edges, or well, it does not even see the edges. So you need something else, and this something else is vector H1 to a very high order, and then basically you kill the entire degrees of freedom, and you only use the degrees of freedom on the edges. And here we use exactly this. So we invert the matrix only on the beta ray that is defined by the edges. Okay, that's really it. Okay, compose everything, and then we need, because of the theory, otherwise it does not come, the penalization on the boundary. I'm not going to go into details. We skip this one, we delete some zeros, and then we need our penalization term. Now the penalization term needs to be big enough to push away all the how's it called, the eigenvalues and eigenfunctions that derive from this bad part. Okay, so okay, great. As I mentioned before, now to create our matrix, to approximate matrix A, we need some preconditioner. We need a really good preconditioner this time. And the really good preconditioner that we can choose is something that is a patch that is big enough to encompass all the degrees of freedom coming from H curl diff. In this case, is a closed edge patch. Okay, that's really it. And thanks to NGSolve, I think that you did not explain this morning, but you just need to extract a list of lists. You throw it into NGSolve with create a block smoother, and you're done. So great. Okay, and here, as I mentioned before, now you can create the sparse matrix, and we can create the sparse matrix from the big system with the penalization term. So here the tilde is the approximation of the A. Okay, so it's done. We can look at some eigenvalues of so how good our matrix P, C, and M, C, D is, and we see that the condition number is 8. So it's a good condition number for a matrix. And now the idea is that, okay, at the beginning I told you this eigenvalue problem is complicated, but the complicated part is here, let's say, from the theory point of view. So we need a patch that is big enough to contain the whole null space of the Hessian. And this is going to be not anymore the open patch of each vertex, but it needs to be the closed patch. And why? Because at the beginning I told you that if you take, for example, one head function, then you are gonna find something that is on each face, okay? Even the faces that are on the opposite side of the vertex. So you need a patch big enough, and this is how you create the patch. So close vertex patch, easy. You can extract the smoother in the same way that I did before. We can check if the eigenvalues, basically the biggest and the smallest eigenvalues are good eigenvalues, and if they are good, then we can use it. In particular, this function, I think that it uses an Arnoldi. No, what does it use? This is a Arnoldi, right? And yeah, in the Arnoldi, we know that if you have multiple eigenvalues, then one gets pushed to 0. So it's not anymore a 10 to the minus 8 times 20, but it's going to be so divided by 20 divided by, but it's going to be 20 divided by 0.2. So good, fair enough. We throw everything inside the log PCG. We let the log PCG run, and we see that after, let's say 30 iterations, I don't want to stay here too long, it gets lower and lower, and it should hit something like 12. And let's wait a little bit more, but yes, it should go close to 12. And then we can visualize different number of eigenvalues. And in particular, we can start with, I don't know, just 0. And 0 is going to be this one. Now, you are not very satisfied about the quality of the image, but just to let you know, we are trying to go from H-1 to something in L2. So H-1 is difficult to visualize. Okay, but this is one eigenvalue. You can visualize some, let's say, some component of this matrix. This is one component. I did only 30 iterations, should be a little bit more. I think that 100 already is quite good. I don't have time. One nice thing that I want to point out is that if you go from 0 to 4, okay, so the first 5 numbers, you have something that looks like a bubble, yeah. And if you go up to, let's say, to 5, so this is the 6th eigenvalue, then you already have something that is really bad. Now, I did very few iterations, but here you should see that the bubble is not anymore a bubble, it's 2 bubbles, okay? So this is exactly what you would expect from, for example, a Poisson equation. So the first eigenvalue is a bubble, and then the second eigenvalue is not anymore a bubble, it's like 2 bubbles, etc. Yeah, okay, the quality, as I said, is not good. We can try to understand how big is the eigenvalue, and the eigenvalue as expected is 1 because every time we need to normalize it. Eigenvector, sorry, eigenvector. And if we print, for example, the thing that the part that lives on the edge, the part that lives on the faces, this part here takes a little bit, but is going to be 0. So we try to go really from h-1 to L2, and this is more or less the problem that we are trying to tackle, and this is how you should tackle it. And yeah, that's it. I don't know if we want, I can try a little bit more, but to do some more iterations. But I think that we need to take a little bit of a break after the question. Thank you.
Some questions?
Yes.
Yes, maybe I missed it in the beginning, but like, what is the application use cases? Like, what are you targeting it?
EB equations, right?
Yeah, so the short answer would be the B equation. Why? Well, the B equations are a natural discretization of an object that comes from the linearization of gravitation the gravitational field, or of linearized gravity. That is the.
You can explain the E field. What is the E matrix?
Yeah. So okay. In a differential geometry, especially in general relativity, you have this Riemannian tensor. Okay, so the thing that we said, okay, we can calculate easily with NGSolve. And the Riemannian tensor is something that is a tensor, a 0-4 tensor. Now, it has a twin. This tensor is called the Weil tensor, and this Weil tensor is used when you do computations in empty space. So the merging of two black holes, for example, is an empty space. And to study this tensor, the E field is one part of this tensor, and the B field is another part of the tensor. And the linearization is actually this formula here. So if you really solve this problem, you could really find the modes of vibration of a black hole in empty space. Still a lot of work to be done, but this is the.
And there is more available on the black holes and
yeah.
Other questions? From my side, some comments on the NGSolve side. So it's been starting my we had the RAM sequence. I order H1, H2, H3, H2, and so something I'm happy. Okay, somehow complete. But then with Christoph said, no, there's facet spaces and. To have facet normal, facet tangential spaces, and then somehow it got boring, it was complete. But then we asked it and filled it with the HCD spaces, Michael with Reggie spaces, and it continued to that some spaces got some applications. And this was the latest reincarnation of the need of more spaces. These are now Hellenhammer-Johnson spaces mapped to faces and edges and so on. The next extension to some more very natural spaces came in. So it's interesting. If we do not add these feathered spaces, what happens? If you only use the element-wise Reggie elements for
that's in this case I don't know, but I ran a simulation for this part. So the time-dependent part, okay. And you see that you don't hit an exact sequence, so the energy at some point blows up. You really see that it's not an exact sequence. But, yes, please.
I have a question on the definition of your H-curl diff.
Please, I wanted to trim down the... Okay, yes, please. Yeah, it's yeah.
You wrote here diff eta and H minus 1.
Yeah, I wanted, because when I was preparing the slides, if I were adding the times V and times blah blah and times blah blah, then it was going up from the slides, and I didn't want that. That's the only reason why.
Okay.
Okay.
It's angle condition. It says it's same space.
And yeah, one thing that I wanted. Yeah, that's
Okay, I think coffee is waiting.
Yes. Yes.
you can publish on the web and have your private favorite NGSolve application online for everyone.
Yeah, thank you for the introduction. So I will show you yet another try to revamp the NGSolve graphical user interface. We had this before on another user meeting, I think in Göttingen, at least once. There we developed something based on OpenGL, so recent OpenGL and Qt, but not really used, and now there is the next try. So in between there came the web GUI, which you already used in the Jupyter notebooks. And now we started another project based on Web GPU, which is a successor to WebGL, which is used for Web GUI, which runs in the browser. And since it's quite recent and still a draft technically and not really released officially, it's not supported by all the browsers. So basically we recommend Chrome on all the operating systems. On Windows, Chrome is just working fine, a recent version. On macOS, also Chrome is working fine. You can also use Safari Technical Preview, but that's a bit more involved. You have to get that and then set some extra flag. And on Linux, it's the most difficult one. Yeah, unfortunately. There you need the Chrome beta version. So depending on your operating system, you get some development or, I don't know, beta package, depends. I cannot edit here. And then you have to start the Chrome with this flag, and then you have to go to this site and enable a feature which is called unsafe web GPU support. So once you have that managed, you can check if web GPU is working by going to webgpureport.org. And there you can see on this browser, on my machine it's not working because it says web GPU appears to be not supported. And to let you know how this looks like, in another browser it looks like this, and there you see different devices. So I have some high performance device, which is based on an NVIDIA graphics card, and I have a low power device, an Intel, and some fallback. So if you see lots of options, then it's working, and if you see some red text, then it's not working. And you need to adapt some changes or use another browser. Okay, once you have that settled out, you can download. So let's go back to the thing. There is two other steps. First, at Wolke, you need to download the latest. I really mean latest because I uploaded another version about 50 minutes ago. I don't know exactly. So the ones I tried in the last break maybe want to get the latest one.
I mean, the one before is also not so bad, right?
Yeah, but it's better to have that one. No, it's basically just introductions with different more options. So I will, okay, let's just overwrite that here. So download that, unzip it, let's remove the old one. And then I go into that one, and here I start the, okay, make it a bit larger, the Jupyter notebook with the index file. And on my machine, the default browser is not the beta Chrome, so that's why I just give no browser. So it won't open any browser, but wouldn't hurt so. But then you get this link, and then in the correct browser, you just open this link, and then it will run the Jupyter notebook. But that's only needed on Linux. For the Windows and Mac users, you can just, yeah, Mac, maybe you have to take care that it's opening in the Chrome. Okay, now we have this link, and now we go back to the Chrome, and we copy this, and then we're here. And now I open this index, and yeah, that's new in the recent one, because here you can actually install all the packages, although you might want to add web GPU. Just to be sure that it's also upgraded, because there's a very recent version of these packages.
What means very recent?
Yeah.
Not 15 minutes, right?
No, not 50 minutes, but about 50 minutes. Yeah, I won't run that now here because I have developer installs and I don't want to mess around now. Just to be on the safe side. But if you run that, it will upgrade all the packages and then it should work fine. Okay, then let's just get into it. So basically, you can, yeah?
Yeah, I see that.
It's in the index. So if you download all the Jupyter nodes, yeah, then you need to download the latest version. Yeah. Yeah, and maybe add Web GPU. That wasn't there. So if you have an old one, this one will be upgraded. Yeah, but it won't be upgraded, all the dependencies. That's the point. If you have, yeah. And this will be needed for the next session, which will be done by Christopher. So that's about app development, and these packages are just for the Web GPU in the Jupyter Notebook, basically. Okay, so the quick start. So how you can use it? The simplest way to use it is to import NGSolve Web GPU to Jupyter. There is a draw function, which can be used similar to the Web GUI draw function we had before. There are not all the options available that were implemented before, but we will get there that we have a kind of a similar syntax. Yeah, and with that we can generate a mesh, and now we have these, okay, a bit smaller. And now we have the cube. We can rotate, move it around. We have some clipping, which you can enable, but then we have to set some point, yeah. Okay. I mean, this is very raw right now. There is still time to refine. So all this is a bit experimental, but we will get feedback and implement more features as we go. Okay. Yeah, another thing, you can also draw a function on a mesh.
Should we ask if everyone is on the same page?
I mean, if it doesn't run for anyone, we can fix it afterwards, and we have another session tomorrow morning. So then
yeah, we will have another session tomorrow, which will go more into detail. So if you follow like this, and maybe there is an issue, we can also sort it out later. But if you have an issue now, maybe raise your hand and Christopher can have a look.
So should we do the same?
Yeah, if you want, you can. But you can also just watch and try it later or whatever. Yeah, you can. You're free to ask questions.
How many have this running?
it's not so bad.
Who needs some help?
Maybe let's wait 5 minutes.
Okay.
And everyone needs the newest NGSolve version. If someone hasn't updated NGSolve for the last month or so, then it might give this mesh doesn't have a curvature, get curvature.
Is the newest from Monday or newest from?
No, that was added 2 weeks ago, so it's not so critical.
Ah,
2504.
Okay, ja, das ist.
It should work on Visual Code on Windows at least. On the others, it's using not the Chrome browser. Yeah, on the Mac, I think it's not working. It is working. Okay, so on Mac and Windows, it's working with code, but on Linux, I don't think so, because it will use some Chrome for visualization, but not the beta one, and you cannot change the flags, I think, in the code. Pardon? Well, the deformation, what's new here, before you could add deformation, but now you can visualize one mesh, add deformation of another mesh, and still it's evaluated on the GPU. So that's the new stuff. So we are much more flexible now with the Web GPU. I will come into that later. Another flag you can give here is subdivision. So that's the number of points it will, or number of sub edges it will use per edge. So if you give 1, then it looks like this. So it's just linear for the deformation. And if we give 20, then it's not working. Let's see. That's strange. That worked before. Let's restart the kernel. Yeah.
Do we find the options already somewhere, or
You can do help on the draw function. That's and there you find the parameters explained. But for instance, the subdivision is already missing. So I mean, it's there, but it's not explained yet. You can also give the size. Didn't try to change that recently, so. Pardon? Yeah, it's also with 20. I tested 30 now, so it's also working. So it's subdividing each triangle into 900 sub-triangles, which is already quite heavy. So don't do that with large meshes, but yeah, it's still working fine. And then it will, for each sub-triangle, it will evaluate the function for the deformation on the GPU and then deform the triangle on the GPU. So who is trying to get it running and can't? So not so many anymore. So I have the feeling some people already think about something else. So maybe we continue. So
continue with the next.
Yeah, I will continue. So now we saw this quick start with the draw function where you can use it as the web GUI before. But what's now better than the web GUI before? The web GUI was written actually in JavaScript, and we had this draw function as an API to the JavaScript library behind. And that was a bit difficult because it was very hard for people to actually change something in the code or extend it. We saw some GS code argument there. So this draw function had a lot of arguments, and some of them were documented and some of them not, and some of them were quite flexible but not so easy to use. And that's also something we want to overcome here. So the nice thing here is, although it's using WebGPU, which is a JavaScript library, all the code is written in Python. So it's very easy to just derive from a class and do something with it. I will show you some examples. And then you can do lots of stuff that wasn't possible before. So the draw function is just the easiest entry point. But you can use all this in another way, and that's what you will see here. So in the background, when you call this draw function, it will actually create some render objects. That's what we called it. One for the wireframe of a mesh, and one for the surface elements, and one for volume elements maybe, or a clipping plane. And here you see how to use them. So that's, for instance, one class that has that's naming mesh elements 2D, that's showing just the surface mesh. And the other one is just showing the wireframe. So by creating these objects on your own, you can already decide which ones you want to see and which ones you don't. Or you could even say, I want to show the elements of one mesh and the wireframe of another mesh, if it makes sense somehow. And to not waste too many resources, we have these mesh data classes. So there's a mesh data and the function data class. And these are responsible for managing the memory on the GPU. So when you create this object, and so later on when it gets updated, it will actually evaluate or fetch all the data from the mesh and then allocate memory on the GPU and move all the stuff there. And this is then used by this renderer and this renderer, so they will use the same memory of the mesh. Yeah, and you can also, for instance, have your own clipping object, which has the clipping plane, and then pass it on to multiple objects, which means they will share the same clipping settings, which is usually good. Sometimes maybe you don't want that, So it's up to you to set it. So you can clip only the wireframe and have the elements shown, or the other way around. Okay, yeah, the rest of the code is actually quite easy. We create a sphere, we curve the mesh, we create this mesh data and clipping. And then we have this mesh elements 2D and wireframe. So here you see the sphere. And then we are drawing. This draw is a bit of different draw than we had before. This is the so-called the core package, which provides just enough to draw something, but doesn't know anything about NetGen or NGSolve. And here you can just give this draw function a list of these render objects. And you get a scene, and this scene has a GUI, which is this controls thing here. And then you can say to the clipping thing, add your options to the GUI, and then it will add this here, and then you can enable the clipping, for instance. And if we just try that, remove this here, and render again, and now we enable the clipping, then the clipping is only applied to the elements, but not to the wireframe. Because if you don't pass an object, it will just create its own in the constructor and has its own settings. Yeah. You can also show 3D elements. That wasn't there in the web GUI, but would have been possible actually. We just didn't do it, I think. So there you see the tetrahedral elements, and we have this shrink. That's part, yeah, that's the volume elements, so that's the mesh elements 3D object, and this has also add options to GUI, and then we get this shrink slide, and then we can look at this. We can also do clipping, and then have a look at the clipped elements. So that's that, and we can also do mesh deformation. And that's where first time the function data comes in. So the function data object stores just evaluated coefficient functions on a mesh. So it gets as an argument the mesh data and some coefficient function. So this will be used when we draw functions on surface elements, or if we want to do clipping or whatever, but also if we want to deform the mesh. So we can just, to the mesh data, attach some deformation data, and then it will show the deformed mesh. That's what you see here. And as before, you can set the subdivision. I think that's done by the mesh data. So if we give 10, then it should be a bit smoother. Yeah. So that's how you can visualize a deformed mesh. So again, as I mentioned before, but maybe not all of you heard it. When we have this deformed mesh, it's actually now drawing 100 sub-triangles per triangle. And then at each vertex, it will calculate this deformation function. So it will evaluate the deformation function on the GPU, and then deform the triangle such that we get this smooth visualization. So there's no CPU time involved anymore when rendering this.
But before the data is still interpolated in bench time, you wait for something else.
Yes, so once we have on the CPU, we have to evaluate the function and transform it to some basis, and then this is the data that's actually shipped to the GPU.
Order there, like you put it
Yep.
into a bench and polynomials over time.
So we can also give order, okay, order 1, something's broken. Let's try 2. Yeah, 2 is working. But there you see it's already the normal function, normal vectors are already some not really smooth. Yeah. Yeah, another thing is point numbers. That's just for convenience. You can, here we have the wireframe and these point numbers renderer. There you can give a font size, and then you can look at the point numbers. Okay. Sometimes something seems broken, then I have to restart the kernel, but I'm not sure why this happens. Let's try again. Yeah, now we have the huge numbers. Okay, and the same thing also applies for visualizing functions. So we also have renderer objects. So here, the most important one is the CF renderer that's evaluated on a surface. And there we again give this function data object. And by default it creates its own color map, and there you can set the min-max, and then you can visualize a function on, in this case, a cylinder or some surface mesh. Yeah, and here it's using order 5, so it's quite smooth. Any questions so far? Okay.
What to do when we get a gray box?
A gray box, yeah. Try to restart, clear the output and restart the kernel. I have that sometimes, and I don't know why. We have to still work on that. So one thing you can try is pressing F12. Okay, although the yellow thing is from Jupyter. But then if you see something right here, then maybe you get some error messages. That's the developer console. Okay, what we are already...
Can you copy an object?
Pardon?
Can you copy an object somehow?
You can actually pickle all those objects and unpickle them. So...
I mean, more like making a copy of one rendered object and then deform it to have two in the same view or something like this? Not yet. Okay. Just
not sure if that's easily possible. You can just create two objects.
yeah, sure. The same.
If you want to move them, I'm not sure if you can. I mean, you can have different camera settings, but that would mean different scenes then, I think. But we have this idea that you, for instance, also have two viewports side by side, and then you can draw multiple objects with maybe the same camera. That's on the list, but not there yet. Yeah, what we have already is the clipping CF. So you can, as in the web GUI, clip through a 3D object and show the function on the clipped volume elements. So when we change the clipping here, then it will move around. And
here IO is possible, right? I mean,
yes, so also with deformation that's now working because it's subdividing on the GPU, cutting there, and it's way more efficient than the WebGL implementation because WebGPU allows more computations to be done and other data layouts. We will come to that. Yeah, and what's also there already are field lines. So there we are basically using the same code from the WebGL implementation to generate field lines using the CPU. So that's not calculated on the GPU. And then just drawing some cylinders on the GPU with some colors, basically. Yeah. So here we have this cube as before, and on this cube I just have some vector field and then show these field lines.
And the axis? Is it possible to draw?
Yeah, it's just missing. We'll be there by tomorrow. That's actually not a huge thing.
and the NGSolve version 2.
Yeah, it's something development. Yeah, and another
NGSolve logo, I think we should put there.
another request we got 2 days ago, which would have been needed by Jay today, is surface vectors. So we have that already since, well, we fixed the last bug on midnight. So I just have a sphere and some vector field. That's nothing special, just something to visualize. And then we have the surface vectors renderer where we give the function data and the mesh data. There's not many options yet, so lots of it is hard-coded. It's still not fully reusable, let's put it like that. Yeah, and then we draw the wireframe and the surface elements, and then we see vectors on the surface of the sphere. And yeah, for instance, here they are scaled by the value, so we have a color map, and then we scale them a bit to make it even more obvious where large values are, but yeah, that's easy to be changed. Okay, so now I showed you all the things of this NGSolve WebGPU package, and then there is this WebGPU package, and we decided to divide it because maybe this WebGPU core functionality is interesting for other people too when they want to use WebGPU from Python and Jupyter notebooks. And this doesn't know anything about meshes or NGSolve. So it has some basic features like the color map, clipping, and this render functions we use actually for the field lines, for instance. So that's what I will show here. But maybe I will get into, let's see this first. So here again, a quick tour. So this web GPU is a new API. It's running in the browser and using written using JavaScript from the API, but we provide this Python wrapper, so you can use it from Python, and each function call actually in the background will be sent to the browser front end, will be interpreted and evaluated, will send the results back, and that's what you get in Python then. Yeah, and here's some useful links. One I actually showed you before, that's this web GPU report where you can check if it's working. For the ones really want to get deep into it, you have the specification, but that's not really easy to read. So that's the whole language and API specification. What's easier to read and do is this WGSL tour. The thing is, when you want to write your own renderer, you have to, in most cases, you have to write the code that will be executed on the GPU. So that was in part possible on the web GUI, but not really easily. And that's something you have access now to. And that's a language which is similar to Rust. So it looks like this, where you have to write vertex and fragment shaders. I will show more tomorrow if there is interest, and I will show you some quick examples now. But in this tour, you get all the functions that are available, or most of them, the data types, expressions. So that's an easy tutorial to get into it. Okay, yeah, let's actually continue with this now. So we have this. That's a very, very simple renderer object just for demonstration in the base package where you just draw triangles. So we have 3 points. We give them a color, and then we draw it, and now we have a triangle. So that's the hello world for computer graphics. It's like Poisson, the unit square. For computer graphics, it's a triangle. And now we can actually do this on our own with the shader code. So that, okay, I want to make it a bit short. So basically you have to write 2 functions. One is the vertex shader, which will be evaluated for each vertex of the triangle. And you have a fragment shader, which will be evaluated for each pixel after the triangle is on the screen. Already projected, it has a number of pixels, and for each pixel this function will be called, and it just returns the color of the pixel. So in this case it's hard-coded, but yeah, in other cases you can calculate that with shading and whatever. Okay, and that's the full example to get this running. So we have this, we import this renderer, that's the base class. We have some shader code where we have a vertex shader which has hard-coded positions for the triangle. So no data is copied to the GPU now, it's just hard-coded there. And just by the vertex index, that's an input, so the first or second or third vertex, we take the position and also the color of this vertex. So we have 3 different colors. And then the thing is, the output of this vertex shader will be interpolated between the vertices for each pixel. So you have these barycentric coordinates, and then you have some interpolation. And then you get this input, that's this data structure here, which is basically position and color, but we only need the color actually. And then we return the color that's interpolated. Yeah, and then we create this class. So the most important thing you have is the number of vertices you have to set, a bounding box just to set the camera correct in the beginning, and then a shader code. And with that you can really write your own web GPU rendering class without any boilerplate. So most of that is hidden behind the scenes, but you can access it if you need to. So with that we can draw, and you can see now a triangle with 3 colors or interpolated, and that's because we have these 3 colors here. The 4th value is the alpha value, that's transparency. Yeah. And maybe strange for you here, we have 4 coordinates. That's because that's normalized screen coordinates. That's more as a computer graphic stuff. That's how transformations are done, because it's using, yeah, we don't need to get into details here. But the thing is, we have hard-coded the coordinates in the screen space. So -1 is the left end of the screen and 1 is the right end. And that's hard-coded where these pixels are, or where these vertices are. And that means now we cannot rotate anything. I cannot move it around, I cannot rotate it. For that, you have to apply some transformation to actually see the camera, the projection matrix, and so on, and apply it. And for that, we have some convenience functions. Oh, first, another thing. We can already combine our renderer here, up there, with the triangulation renderer we saw before. And then we have 2 triangles. So that's the one we do with the hard-coded coordinates, and in the back you have the one where the camera actually works. And to make the camera work on our implementation, we just have to change 2 lines. We import the camera. That's a kind of custom syntax, so we wrote our own small preprocessor for shader files. And this will provide this function, camera map point, where we give the coordinates. And now these coordinates are 3D coordinates in space. So that's the usual coordinates you're used to. That's why we have now 3 coordinates here. That's what we changed. We have this import camera up there, and we call camera map point. So that's all we had to change, and with that we can draw the triangle, and now we can rotate and move. Yeah. And the next step would be, but I don't know how much time we have, but yeah. The next step is we don't want to hard-code the coordinates in the shader because that's not really useful. But we want to allocate memory on the GPU and move some coordinates there and then use it. And the way to use that is called bindings. So you identify global variables by just a number, and then so that's the shader code. And there we say there is a global variable, so that's variable storage, meaning there's the different types, there's uniform and storage, but storage is used for large arrays. And it's called vertices, and the data type is an array of type F32, meaning floating point, or single precision floating point. So there is no double precision yet on the GPU, or on web GPU by the standard. So for visualization, all the time it was using single precision because usually it's enough and it's more performant. Yeah, and we have 2 arrays, global arrays for the vertices and for the colors. And we access it just in the C syntax by using vertices and then bracket and some index. So 3 times vertex index plus 1, or yeah, vertex index plus 1 plus 2, because we have 3 values per vertex. So and that's the new code. We have these 2 declarations of global variables, and here we are just using them. So that's the GPU shader side of the changes. Now the other thing is we have to actually, in Python now, generate the data and move it to the GPU. And that's done, okay, we get some points and colors now as inputs of our renderer class, and then we create NumPy arrays. And there we convert to float32 to have the same data format so that we can really do a mem copy. Yeah, reshape, but that's not really necessary. That's just to access it later on. And then we implement this update function, which was done, so that's an override of the base class, and there you do all the GPU stuff. So in this update function, you have access to the actual GPU already. You don't have that in the init function because of the initialization timings and so on. And also to make it work that you can pickle the class, because there is no GPU buffers allocated after the constructor. But when you have that, you already move stuff to the GPU. And there is this convenience function we provide where you just say buffer from array. It will take some NumPy array, put it or convert it to some memory chunk, and then just move it there. And after that, we have to tell it somehow that this array actually is the one with the number 102 in the shader, and the other one is 101 and 102. So we have to identify them somehow, and that's done with these bindings. So we have this get bindings function, which will be called by the scene rendering, and then we see just buffer binding with the number, so it has to be the same number as in the shader, and we give the buffer. And with that, everything's done. So now we can just create the points and colors in the Python side. We create this object, and we put it in draw, and then in the draw it will call the update, and it will call the get bindings and everything, and the get shader code, and then it will draw it. Yeah, so now that's working, and now we can try to just change one coordinate. yeah, now it looks like this. So it works. And the last thing in this section I want to show is how to actually create something in these controls we have here. So it's still empty, and we saw that some objects actually provide add options to GUI, but if you want to do that on your own, you can do that too. And for instance here, that's actually not really needed, that's only for exporting notebooks. So we draw something and then we get the scene, and the scene has this GUI object. So the timing is important because before drawing something, this GUI object isn't actually existing, so we have to do that afterwards. And then we call slider with some value, a callback function when the value changes, and some min-max and a label. And the callback function, what it does is it changes the first coordinate of the first point in our triangular input we had before. And then it calls scene redraw. That's actually, we would like to do it different now, because what the redraw does is it updates all the objects. So that's the redraw. When a grid function changes, we actually have to evaluate it new, copy the data to the GPU. But we can also do it differently, but yeah, let's show it like that now. Is that working? We still have the odd. Let's revert that back. Now we have the error again. Second.
What am I doing wrong when I don't have the slider? It just says position.
Yeah, that's the slider.
That's the slider, is it
No,
not?
I don't have the slider.
Oh, let's have a look. Let's have a look. You don't have this?
No.
I'm not sure what's going wrong. So you should have this, and if you change it now, then it will change the position and redraw, and yeah, now you can play around.
Ah, okay.
Is it working?
Yeah, you have to be careful with the zooming of the windows.
Oh, maybe that's.
Okay, yeah.
Yeah, maybe it was just hidden. Okay, that's that so far. Yeah, maybe just a quick note on that. Another renderer object we provide in the base object is this so-called shape renderer, where you give some simple shape like a cylinder or an arrow or a cone or whatever. And the idea is you have some interface where you can just generate data where these objects are and in which direction they point to and which color they have or a value. And then you can draw many of them. So that's just a convenience thing. And with that, we could do the coordinate cross, for instance. And we're using this for field lines, where we just generate the data for the field line somehow, and then we plug it into this renderer, and then we can draw it. And the same thing is done for the surface vectors, where we have a shape for one arrow or one vector, and then we just generate data for points, and then the shape renderer is used again. So that's a very modular design where you can reuse the objects, and you just have to feed it data from somewhere, and then it does the thing. Yeah, here, for instance, you have the arrows. So there you see the coordinate crosses. It's not really, not much work left to do that. Yeah. So there we generate just a cone and the cylinder. We move it, and we can merge them, and then you have this data where you can draw the arrow.
And text.
Yeah. Yeah. Text we have too. So what's the next thing? Yeah, and you can also, that's needed for the field lines, you can also add colors or values to them, and then they're using the color map for giving them the actual color.
They also see how you use a different color.
Yeah, there you can see we're creating our own color map. There are some hard-coded values, but actually you can generate them with some Python libraries on your own, and then just pass it on. Yeah, that's maybe just first the compute shader. That's interesting. So that's one main point why many things are so much easier with WebGPU than WebGUI or WebGL before. Now we have compute shaders, which means you can run code on the GPU without visualizing anything. You just have global variables with some buffers with input and output, and then you can generate data actually on the GPU. And we're using that when we do the clipping planes, for instance. So we cut all the volume elements, and then we store the triangles that will come out, and that's only done once when you re-render it, we don't have to cut again. In the web GUI, we actually have to cut all the volume elements in every frame we render, which is quite inefficient. Yeah. So here is an example. I won't go into detail. We have two arrays with 1, 2, 3, and 4, 5, 6, and the GPU code adds them together and stores the result in another array. And then we read the buffer that we allocated before with the values, and we will get 5, 7, 9, which is the sum of 1, 2, 3, and 4, 5, 6. So the buffer binding, that's basically the same thing we had before. You have to give the numbers and everything. We have one that's a uniform that's used for global variables which are small. And for large arrays, we use the storage type. And for one, we have to specify read-write, because that's the one where we actually store the result. And the other ones are just read-only. Yeah. And the rest is basically the same thing we had before, buffer from array. Here, there is no convenience function. We have to allocate the result buffer with some size, and you have to give it some flags on how to use it. And that's saying that's a storage buffer, which means it will be used as a storage like this. And copy source means we actually want to look at the values from the CPU side. And you have to tell it in advance, because the GPU driver will do some optimizations, and it won't allow all the operations on every buffer you allocate. So you have to be careful to set that correctly. Yeah, apart from that, there is this convenience function from us again, where you say run shader code. So that's the shader code. And then so that's a bit like CUDA and GPU programming. So the threads on the GPU are organized in groups which work together, and there you have to specify actually hard-coded how large the groups are. And then here you just say how many groups you want to allocate. And I just say, I want to round up the number of the array, so the size of the array, to the next number of groups that's needed, so just to have enough. So we actually start here 1 thread per entry, which is not really efficient, but it's just an example. Okay, and then there is one more thing I want to show, and that's selection. So what you can do too is, we have now 2 of these shape renderers. So we have cylinders and cones. That's where it's just created by some convenience function. We now have 2 different color maps, and we also have color bars. And that's the thing that you see here. So the color map itself is just the mapping from a value to a color. And if you want to visualize the color map, then you use this color bar structure, and there you see it's also possible now to have multiple color bars and color maps available, and there we just generate it. And then when we draw the color bar, where is it? Oh, here it is. We just give it a position, which is again the normalized position, so -1 is on the left and 1 is on the right, and in y direction 1 is at the top, so we just move it down a bit. And we have also labels where you can draw text on some positions with some font size, and here we have the cones and the cylinders. And the first one is just reserved for later. We'll see that, that's at the bottom. And that's how I draw these 2 color bars, and on the right some text, for instance. And what's now possible is that this shape renderer implements some functionality that you can select it. So you click somewhere, and then it will tell you on which object you actually clicked and at which position, maybe. Depends on how you implement it. And that's done with this, you just say onSelect and give it a callback function. And the callback function calls this set label, which sets the text, selected cone, and you get this event thing which has 4 values, or 3 values actually. And then you can call for the first value as an integer, and the second value as a float. Because you have to know, it's basically just a memory chunk, and you have to interpret it right. Yeah, but the set label sets the first text. Then it calls it that actually you tell it you have changed, and then the next time it renders it, it will update the data and copy it again to the GPU. And then we just call scene render. This approach is more efficient than calling scene redraw, because the redraw will update all the objects. And here we will only update the label object. Okay, so we already did that. And now, let's make it a bit smaller. If I zoom in and click somewhere, then we have here selected cone 2. So it is the second cone with this value. And then we can, here we have the cylinder. Yeah. So that's some nice thing you have here. And again, as before, the web GUI also had something like this, but it was hard-coded by us and it was not really flexible. And here you can actually change that. Maybe here I skip this how it's working. I will only show the example how to change that. So a bit larger again. We will create our own shape renderer class and we change the selection behavior. And we do that by setting this select entry point, which will tell it which function in the GPU code is actually responsible for the selection, because we have to have a special fragment shader for this case. And we just change that, and we overwrite the get shader code, we take that off the base class and attach our own shader code, which is just these few lines. And here we have our my select shader, and there we return a vector for integers. That's just given, that's the data format we are using for this, for each pixel, for the select buffer. And the first entry is special, that's telling the scene which render object actually was selected. And the other ones, the other 3 values are free to use. And here, for instance, we take the input, which is the output of the vertex shader, and then we take the position. So now we have x, y, z coordinate of the actual pixel we clicked on, for instance. And to make it integer, we do this bit cast, which is basically a reinterpret cast in C++, just to map the data. Yeah, that's all. So you only have to change this, and then we create this instance. Again, we have this labels thing, and here our callback. And now we're just saying selected my cylinder at point, and this is the vector of these 3 coordinates we had before. And then again, set needs update and render, and then we set this callback function. Is that needed? Oh, yeah, that's. Do we need that? I'm not sure. Anyway. Okay, now I think something is strange. Let's restart again. Now we have to do the first. Now I have the scrolling thing you had too. So I need to reload the whole. Yeah. Yeah, so now it's working. So now we have selected my cylinder at point, and now we get these 3 coordinates of this point. Any questions so far?
Okay, this might be a stupid question. Is there going to be an API tutorial? Because there's already a lot of stuff here.
Yeah, that's part of the documentation now. So we started with examples because that's easier to keep updated and have something. The whole package is not very huge. So if you look at just all the classes that are available, or if...
It's a Python file?
Everything is Python.
Yeah, everything is Python. So you don't have to look at some strange. So the whole code is on GitHub.
Except that the shared, of course.
Yeah. So if you look at the repositories, you will see, let's first look at the NGSolve. NGSolve Web GPU. So first hint is looking at the init, and there you see which objects are imported, so you get some sense what's available. And then just looking at the constructor of these elements, you get an idea what they expect. So that usually helps a lot. And we're using type hints and so on, so it shouldn't be too hard. If you really want to get in, yeah. If you really want to get into the details, in the Web GPU repository, there is this Web GPU API file, which is actually a one-to-one wrapper of all the JavaScript API in Python with type hints and everything. So you have all the enumerations and stuff like that. So for instance, yeah, backend type, and you have all the options. So And that's also very convenient. If you really want to do the web GPU by hand, you get autocomplete and all the options and you see what's expected. Because we had another interface before where you would just pass dictionaries from string to string and then, yeah, you have no idea why it's not working. Yeah, so that's really the web GPU
So
thing.
what's the overall plan? This will be the standard output in a year or a month or additional just for...
It also depends on the browser support, to be honest.
Yeah,
That's
obviously
so.
But we expect this to change in a few months or something, or?
Yes, so once this is really working by default browsers everywhere, we will kind of skip to that in favor of the web GUI we have now. And maybe even there will be another standalone approach, but that will be Christopher's part, where you build an app. So it's also easy to actually build an app and have your own complete GUI standalone. So independent from the Jupyter thing. So all this, what we see here,
Might be a place
you can use also in the app development we will show later, which is running in the browser. There we also have one component for web GPU, and there you can use this visualization. So that's not only just for the Jupyter notebooks, but also for standalone applications. Let's put it like that.
I think a simple answer to Christoph is, when I'm asking Matthias for some feature for web GUI, then Matthias will not be very motivated to add some feature to web GUI. If you need some new stuff,
then you will have to use this.
Another question?
Is there any way of exporting whatever it is going to generate, or to kind of have it also stored in file somewhere to be...
So there is, actually it is kind of working that you export the Jupyter notebook and then have an HTML which will load.
No, say I want to have my Euler angles and whatnot.
Yeah.
I want to export 50 pictures with 50 specific
Yep.
Euler angles.
No,
What would be the way to do it?
the plan is that you, at least for the render object, it was working. For the scenes, I'm not sure, but that's the plan, that you can actually pickle the whole scene object you get.
No, I mean, I think you were mentioning pictures.
Afterwards.
Yeah. Screenshots is already implemented. Make screenshots from the scene.
Okay.
Or do you mean something else? Because you're talking about Euler angles, and do you want...
No, we want to have 50-50 screenshots, which I can want to write in a Python for loop somehow.
Yes, you can make a Python for loop, rotate the camera a little bit, make a scene.render, make a scene.screenshot.
Okay.
Yeah, that's possible.
And scene.screenshot is...
I think it's scene.screenshot or something.
Yeah.
Same as
I think it's possible to run it headless too. I mean, you can run Chrome headless.
yeah.
Yeah. Maybe a bit difficult, but in principle working, yeah.
Showing with the eye or something.
Yeah. So, these two. Yep.
Okay. Das hat vorher gerade funktioniert. Ja, warte.
Jetzt ist schwarz. Also jetzt glaube ich checkt das.
Nur kurz neu starten.
Aber vielleicht einfach.
Das hat gerade funktioniert.
Nochmal ausstecken probieren. Ja, zumindest ist es nicht mehr blau. Jetzt ist wieder blau und jetzt. Was ist das?
musst du angeschickt?
Ja.
Ich kenne den aber nicht mehr.
Noch ein Report, den du so anschaust.
Es kommt gar nichts mehr. Wir haben es gerade vorher ausprobiert in der Pause und das funktioniert. Also, I don't know. Vielleicht das Kabel.
Wir haben da auch was HDMI.
Ist das vorher schon was? Das Kabel.
Kann man mal, hast du einen USB-C-Stecker? Hast du einen HDMI-Anschluss?
Ja.
Vielleicht ist es der, vielleicht soll man...
Ja, also hast du so einen Adapter auf USB?
Ja, da liegt, glaube ich,
Nein,
der ist nur für... Fast ein bisschen Viere. Aufpassen, dass den Beam nicht. Rest.
Gut.
Zu dritt.
Geht schon.
Okay.
Yes! Okay. Then we can continue. I want to introduce to you a second new thing we have been working on over the past, I don't know, it has been actually quite long already. Apart from the web GPU, which we now open sourced, and I would say it's in a early stage to really test it by you. I wouldn't say that it's a really completely stable release, but we would be curious about your feedback. And it's definitely ready to be used in the first test projects. It's called NGApp since a week or so. And the idea is to make it easier to build some easy engineering applications out of your NGSolve simulations. So basically make your simulation code usable for people who don't want to do Python programming. You find it on GitHub in the SerpSim company repository as NGApp. You also find it on PyPI by installing just pip install NGApp, and with this additional def brackets you get the development dependencies that you will need to develop your own apps. We started writing a documentation. It's not full done, but the first 2 tutorials are there, and there is a API documentation where you see kind of all the objects and classes that are available, and they are also not so badly documented, because basically we wrap them from some well-documented JavaScript library. So let's get started with the first tutorial there, which is we want to build like a simple app for elasticity, so as for solving an elastic beam, like the typical
elasticity first demo tutorial, but wrapped in an app. How do we start with this? Okay, so can everyone read it, or should I make it bigger?
A little bit bigger, please.
Like this? Okay. So to start your first create your first app, what you want to do is go in a command line. The mouse is slipping. And paste this Python -m ngapp create my new app. And wait, I want to do it in some app folder because it will then create the app there. And then, yeah, if you already did that once, it asks you if you want to re-download this again. You say yes, and then you give your app a title. So now we want to make a beam solver, and it will suggest like 2 additional options for you. One is the Python module name. This is kind of like the new Python module that will be created and that will be pip installed. So it should be a name that you didn't yet use in a package or so. So usually, easy addition would be to use your package name _app or something. And then the name of the Python class, which also must be a viable Python class, and it suggests like some names. And then it downloads everything and installs everything so that you can start app development. Here the command is put how you can start the app up. I will just do that. Beam solver, and with --def you start the app in a development mode, which enables automatic reloading and some other nice debugging features. And you already see that we provide kind of like a simple app which doesn't do anything but like have a counter and a click me button. So this is how you start. And now we will open in your editor of choice the folder that you have created. So I put it in apps and then beam solver. So there should be this new repository created where you call this function. Oops, that was the wrong one. And in there is like some PyProject toml, which is the description of the Python package, some GitHub action already, and a source folder. In the source folder you find your module, and in there you find a few files, but the main file that we want to look at is this app.py right now. And I want to tell my Pyrite to track all that so that it gives me auto-completion. And then you see here is basically the definition of this app. So we import from NGapp the app and some components, and we create our new app with some title and some button and some input field. And you see already this like resembles quite closely the app. And if I change something here and if I save the file, it automatically updates the app, and so you have kind of like a live development. I think most of you probably know it from this LaTeX development environments and so on.
But that's only available if you started the app with --def.
Yeah.
Otherwise it wouldn't do the app.
So yeah, like this we can start developing the app. Oops. And if you open the console, every time you save, you will see this reloaded app package and so on output. And if you do print statements and so on, so we can do that, for example, like put here a print button clicked. And now every time I click the button, here this output will come. So this is like all the print output comes into the console, and you can really easily use that also for debugging, because you just, if you don't know what's happening in there, you just put in some prints, and yeah, this helps. So let's move that to the back and go back to here. And how I usually start developing this is, wait, let's move this here. is I first create the layout, and I want to do that now by showing you some of the classes that that can be used. But this is, so we basically wrap here a very powerful Vue, so this is JavaScript framework for creating web applications, which is called Quasar. So if you look at, for example, this Q button, and if you go to the definition of it, you will find out that this is actually a Quasar component. Where we link, for example, here to the documentation. And you see what this thing can do. So you see kind of like the properties and slots you can set. You can see that it can be, there can be added a label and there can be added icons and so on. And you can see here some examples of how these buttons can look like, how they can be customized, how they can be, like for example, if you want to do some icons on them and make them round and make them square and so on. And all that you can do with this package from Python. Basically the only difference is if here is some property like icon minus right, you can use it the same way, but you have to prefix it with a UI and use substitute all minus with underscores. So for example, if we want to have this autocomplete UI icon right, and you see also like autocomplete and so on works here. We can do some icons here, and there you can also use this MDI library for this is material design icons. So I think play is one or not. Wait, I killed too much. There was some. Yeah, no. I think it's also just play. No, play doesn't exist, so you see that this name is not, but I think it's MDI play, yeah. So there is this material icon library, and from that you can use all kind of, and there you can like look up how this icon is called and so on. And then you can use them, and then now you have the like play button with, yeah, I don't know. Start. Wait. With this large. So now we have a play button with a play icon. So, yeah, so if you follow some of the tutorials there are like things like this toolbar, which basically adds such a toolbar, so we can shift the heading into the toolbar and remove this padding here. And now we have some mistake. Yes. That we have to remove because we removed it. And now, now for example, we have such a toolbar which has the background color, our primary color of the app. I will come a bit later to that. And a text inside it. And you see here already that you can nest all these components. So the first arguments of a component can always be different other components which will be put inside of that. So for example, here we have a centered component, and you can put like a toolbar, or we can just make a div out of this here. This is like a typical HTML div. And like that you can nest your components and you can build some kind of application out of that. So I will just maybe copy that now here, so to also show the Q card. And the Q card is basically like a wrapper class that makes kind of a nice card layout. Okay. The next thing I want to show, how to add new components. So we want to add a new length and a width component to the inputs. Wow. And here you see, like you can, I don't know if you see it from here, but because I'm not sure if I can make the app bigger. Ah, yeah, I can. You can add some labels and like a lot of, there's like a ton of stuff and you can just browse through this Quasar documentation to find like, if you want to, how to make the things. But you're very flexible there. And you already hooked up the solve, I think in the, okay, no. And what you can also do is you can build your own new components by deriving from an existing one. So here I create a new class, like my visualization component, which is derived from a standard HTML div. And it contains some WebGPU component which is able to draw. And it also has a certain styling. So I like the WebGPU component to be bordered by some thin line. And if I now add this to the whole component, I get here another component, which is a bit, because I zoomed out so much, which looks a bit big, which already like, you see the border outline and there will be the drawing stuff. And like that, you can kind of like create your own customized components that you can also reuse if you build multiple apps or if you want to have one component in multiple locations of the app and so on. Any questions so far? Yes?
That thing is a web browser? Because for us it's a web browser, but yours doesn't look like it.
Yes. This is a web browser started with --app equals something. And then it opens Chrome in app mode and it looks cooler without like the borders and so on. But I haven't figured out yet on how to use that on Mac, because on Mac it doesn't open. But I think there's a way, we just haven't tried it really. But this is also one of the points I want to come a bit later to. Like it's actually a possibility to build like a standalone desktop app and not only like web applications. Any other questions so far?
So what you showed us here is similar to what you showed us last year. So the main novelty is the deployment right now, right?
No, internally it's very different. Before everything ran in Pyodite. And here we run just in Python. And we connect to the JavaScript from the browser directly via WebSocket. Which means you are not limited to what is working in Pyodite, and you're also not limited to the slowness of Pyodite and so on, and some other problems. Yes.
locally even without any internet connection.
And it's now open source and everyone can use it freely without having to log into our framework. But yeah, from the Quasar point, I think not so much has changed. The integration of the web GPU is also a main part, because that makes it way more flexible to be able to draw like different render objects and so on. Yes, so I will now just copy this part of the code, which is basically what Matthias explained before. Bum, bum, bum. So what do we do here? Ah no, this is the solve. Whoops, I wanted to put that down there. And do on. Ah yeah, and you can like connect some things to these buttons, like with this on button click, I want to call this solve function and query some, like for example from the length I can query the UI model value, and then from the GUI I named it differently. I want to have a draw, and this draw function we can basically implement what Matthias showed. So as a first step, let's just draw a wireframe. I hope I even managed to copy paste everything. So now if you press the play button, you will get a wireframe with like length and width that you put in. Not so much computation yet, but exactly. So this mesh deformation and so on I will skip for now, because like Matthias showed that anyway. You can now implement all the stuff that Matthias showed here into your draw function. So you can for each component have like different draws. So you can, like, if you want to visualize I don't know, mesh deformation from the elasticity solver, you added the deformation to the mesh and so on. You can draw the von Mises stresses or what you want. But it really helps. So for example here, to not always start like with the most complicated part and then set up the GUI, but like just have some helper functions, like, I don't know, use a placeholder, a y coordinate for the von Mises stresses, and draw that for the beginning, and then replace this calculation code with your well-tested code from the Jupyter notebooks. So for example, if we do now this and we get the deformation in, we can, don't want the deformation, we want the von Mises. I don't know why it doesn't format it the same way as in the Docker, but let's make it different. Now the deformation always needs to be a three-dimensional function. Like this, I think should work. Maybe a bit more interesting if the x coordinate is deformed by the y value, then I don't know. Yeah, but you see here, basically everything that Matthias showed before you can use here in this web GPU component. And you can also combine it with these select functions to like click on the mesh and then get some feedback and so on. What is the time? Okay. Haven? At 5 or?
Yeah, maybe 5:15 or so.
Okay. Yeah, And if you continue in this documentation, basically, okay, here this implementation of elasticity so far, I don't think I have to show here. I think you're all very familiar with stuff like that. What is then more interesting is to actually have also some like interactive callbacks. For example, a slider for the deformation scale. So you can have a Q component added a slider with some minimum and maximum value, which you can also, of course, get as a result from your computation and so on. And then say on update model value, I want to call some function, and in this function you can set, for example, from the mesh data the deformation scale and re-render the scene. And with that, if you try it out in the app that you had, you can interactively like deform the mesh with the slider. I want to come to 2 more points, if I'm right. Right. Let me just check my list quickly so that I don't forget any important things. But yes. I would skip or leave that as a, I don't know, homework or whatever, because I think this is quite straightforward with the callback. What is also interesting is the load save functionality. So we have implemented a lot of stuff so that have as little as necessary to do to be able to save the state of your app as it is, or as you want, so which components you want to save. And for this, basically every component that should be stored if the app is saved needs to just be given an ID. And as soon as you give an ID to a component, the storage creates, for example, for all these Quasar components, an entry. Okay, this should be unique, this needs to be unique, else you get an exception, but then the Quasar components on a save and load will restore the value that was in there. And you can easily see that already in the app load and reload, because basically if we do an app reload here, what you will see is, I don't know, I set now the value to 1, and as soon as I change something here, the value will be reset to 3. Because what we do when we do the app reload, we store the app, we load the Python module freshly, and we load the app again. And as soon as you put an ID to this input here, for example to the 5, I think the first time it's still, because it needs to first save it once, but from then on it should be stored. Something happened. Right. Sometimes when bad things happen, you need to restart it. But if it's, I don't know. Okay, that is not the app's. That is my fault, not the app's fault. There is somewhere a 3 inside. Let's start it now. I didn't want here, I wanted it. And now let's save something, and there's something strange still, that there is the 2. But the 2 is restored, but strangely like the length of the style of the label is not. Okay, this is something new. I mean, maybe I destroyed something with my last minute changes. But you saw, okay, at least you see the value is saved, so it doesn't reset. So I don't know. Here I can put the 1. And
yeah, so that one will be released.
Yeah, exactly. The width will be reset, but this one stays. And for larger objects, I hope I have that here now. Yes. For larger objects, so you also want to store the mesh, like some grid function or some other objects. What you can then do is each component has a storage, and you can, for example, after calculating, you can set some things to some index in the storage. So for example, I set the mesh, the deformation, and the von Mises stresses as the solution into the storage, and say use pickle equals true, and then it pickles all that, and on an app component load, I can ask, okay, is there something in the storage that is called solution? If yes, please give it to me and do something on app load. And like that, you can implement not only like store and load for so app reload for the live development, but you can also add like a simple save button, a load button, put it into the toolbar in the top, and then get here a save load button, which allows you, which opens like basically, okay, maybe let's implement that quickly.
These colors remind me of Windows 95.
This one?
No, that's screenshot below.
Ah.
This looks like the very old classic
This one?
Windows.
Yes. Oh, yeah. Good old style. You can make it better.
Yeah.
See, that's why we provide a framework to build apps, because I'm not a good designer. So toolbar. And now we have this save and load button, which opens now like a menu to like store your app, and which opens a menu to load a stored app state. So you can very easily save everything that the user did. And then one more thing, which maybe Matthias explains a bit better, but I can try. After you finish and you created a super wonderful app, if you want to share it with a lot of people, you can very easily create a web-only application from it, using GitHub Actions and using GitHub Pages. And basically what you need to do is you need to additionally put all your dependencies, all your pip installable dependencies into this list in your app config file. So if, for example, if I go to the, I think here's nothing in, right? Yeah, here's an empty list, but here we would need to put in at least NGSolve and NGSolve Web GPU. See, it's a smart one. This we don't need. And if we do that, and we push this as a repository to GitHub, we can then go to the setting pages and activate GitHub Actions. And we already have here a GitHub Action script inside the demo repository, which a workflow, which builds, well, wrong. Which builds like this app as a Pyodite package in the browser. And for demonstration purposes, we have done this here with a finished version from this Beam solver. And it's then, oh shit, I forgot to put the link here. Yes. And then this might load a little bit.
We are missing the gears.
Yes, there should be some info what is loading. Shit, okay, I'm sorry. I pushed some changes that are not compatible with the web version. That is bad for demonstration, but
you'll see it tomorrow.
Tomorrow you can go to this page and see the live version of this beam solver where you can like solve elastic beam for different modulus.
For instance, also the FE Stokes validator app is based on this. So if you track the link on the poster without...
Oh yeah. There we have a live, a working live version, yeah.
Then you see that. But also you have to take care that since then Python is loaded in the browser, that's kind of a stripped down version of Python where not everything is available. So you have NumPy and SciPy, but not all the solvers are available. So no Bladizo, for instance. I think also no Flux, so that's curiosity. Yeah. So you have to take care of how to use that. But that's a way to really build an app, host it on GitHub pages, and there's no cost because it's just a static website and many people can use it.
You can use web app or web GPU or web GUI.
You can use both.
There is also a web GUI component where you can use the drop
people
command.
with older browsers can use it.
Yeah, then it's independent of this new Chrome thing. So if you don't need the web GPU stuff, a new one, you can use the web GUI or even no visualization or just there's even Plotly and Matplotlib also available as component. With that, it runs on any browser.
One small thing, also each component has a .add key binding, which adds a key binding. This might also be useful. This I think I skipped now in the documentation. And one thing I want to engage for tomorrow, I would like to start a little bit of a discussion on which kind of features and which kind of functionality a future version of a NetGen GUI should provide, or how people want to have it. Currently, I see that as a good opportunity that we can have some exchangeable components and everyone can build their own GUI as they want. And we provide a standard one. So I started a little bit with something that could go into this direction. But we can really discuss, and I will also show tomorrow morning a bit more in depth what I did there, and like some features, like for example shared camera views and so on, and like so these tab menus and so on. What we could build there in the future, and like what the ideas of people would be, how this could evolve and should evolve.
Where was the document that you were showing us?
This one?
Yeah.
This is just like github.com serpsim ngapp. So
Here's a link in the Google Docs.
yeah, I put the link in the Google Docs. It's in our GitHub. There is a ngapp repository, and there is a link here to the documentation of it. And there is like getting started, which is describing like how to install, how to create the first app and how to run it. And then there is the two tutorials. One is about building an app and one is about deploying it to GitHub Actions.
Do you have any app to show running live?
Hmm?
Do you have an app deployed on GitHub?
Yes, but it's broken. But also the FA Stokes repair is an app that is. How is the link?
There's someone else in something else. Mine working. NGSolve dev in GitHub.
NGSolve dev.
It's not you.
NGSolve. No, not the person. So for example, this is an app that is built. Is there a link to the validator somewhere here? Yeah, here. Ah no.
That's not the one. Oh,
Just X minus
Here?
Yes.
No.
No, not. At the last, I can't remember.
Hmm?
It'll make it like this if he Stokes.
Ah.
Is it without
No.
repair, I think. If he Stokes validate.
It's F Stokes with minus validated.
If he Stokes
Repair.
repair. Also with a minus or what?
Minus
No.
validated.
Repair, one word. Repair,
Minus
minus,
validator. Did I miss? Wait.
großen Kleinschreibung ist richtig, ne?
Ah, wirklich?
Ja. If Stokes ist okay, dann musst du.
Warte mal. Ah.
Also mine is working. You can also try this.
This.
No,
So.
no, no, no.
Und hier?
Von hier, that's the link at least. Use the link from here. Or minus validated with capital V.
Hm.
That's it. Minus validated.
So. Yes.
Well,
Yes.
don't. Let's wait till it's finished.
Don't celebrate yet.
Yeah, don't say. But
No, should
mine.
Oh yeah. And if you open the, this also might be an interesting part, to open the developer console because you get often like error messages there if something goes wrong.
Yeah, this there.
Yeah. And here you can, I don't know, validate. And looks
How many
good.
points? 8 points.
8 points. Validate the cards of the card game.
Question.
Mm-hmm. Sorry.
Is it fully customizable? So you said that elements are based on HTML. So can I use CSS as I want to, or are there customizable restrictions?
Basically, as you want to. I don't see. So, for example, here you see that in the app you already use some CSS also to modify. So, for example, this UI style, you inject some CSS into the component. There you can do anything you like, paddings, colors, whatever. You can, like Quasar provides like a color theme, which is usually recommended to build apps, and you can set the colors of your scheme with set colors, and then, for example, primary is something, secondary is, I don't know what Copilot now suggests. This is not correct. And now you see it got a lighter blue color from this primary.
I think it will be also possible to inject the custom CSS file, the whole thing.
Yeah.
It's not there yet, but I think that's possible.
Okay. Yeah.
When you mentioned the standalone app, did you mean the user pages app, or can you actually convert that to a installable app?
No, this is now basically a pip installable app already.
Yeah.
What I can also show in the NGSolve app, I even made it then that you create an executable on Windows and Linux. You have like a command line executable, so that I can now start my app with NGSolve and some Python file. And this you basically just do by, let me show. By adding this project.scripts into the PyToml, also PyProject Toml. And then pip creates an executable which calls this main function and which basically looks like a normal execute exe. Yeah, but I mean, in Mac it doesn't work yet. But basically, the idea is to start the web browser in this app mode, and then you don't see that it's a web browser. But yeah.
But it still depends on whatever is set up as a web browser.
Yes, you need a Chrome. You need then a Chrome installed. So I mean, you can use this Electron and so on frameworks, but I'm not really a huge fan because then you need to. It instantly becomes super huge, and most people either have a Chrome or an Edge or a Firefox installed, and as soon as Firefox supports all the web GPU stuff and Chrome and Edge also on our browsers, it shouldn't matter which browser you use, and everyone has a browser installed. Yeah.
So you start this app mode browser with Python-m. Is there, or would there be a relatively easy way to do it the other way around, where you have some Python script that does some computations running, and then you add some patched draw command that spins up the app and draws whatever you want to draw?
Yeah, I think that's possible, yes.
Yes.
Okay.
So that's what the main script does basically, and you do it later on, and then.
I mean, you can do two things. You can either have the program then start up. This is what basically you patch the draw function, and as soon as the draw function is called, it calls this GUI main function in a thread and starts up the browser and so on. Or you start in your main executable a WebSocket and listen to incoming draw calls from other scripts. I don't know.
So you could also run this basically also on the server and look at it locally. So it's automatically you get the server client interface somehow.
Would be very easy to implement something where you run the script on a server and pickle and send the data, the solution to your local machine and then draw it there. But I think this is one of the main reasons why we try to design it now in this way, because everyone in the NGSolve community would want to use it somehow differently, and one GUI then is just a mess. And that's why we say, okay, let's build multiple GUIs in a way that everyone can build their own. Okay. Yeah.
Is there anything GitHub Actions, GitHub specific for the pipeline deployment, or can you just deploy it to any web server?
That's a good question.
Any web server.
It's not too bad, but it's work.
There are some specifics. We can talk about that because it's a bit in the detail. It's about for the communication between the threads. We need this shared array buffers in JavaScript, and the response headers of the web server have to be set correctly in order to make this work. And for GitHub Actions or for the GitHub pages, we're using a service worker to work around that. So it's a bit up, but in theory, it's working on any static web server. So, principle yes, but maybe there are some specialities.
Basically, you need to do some configurations that Matthias did for this workflow actions.
I think now many of us have to think about it and have to write a bit. Okay, come back with questions today, tomorrow. I think you continue to look tomorrow morning on the details on the web GPU.
Yes. Are there, like, if there is anything that you want to see in more detail tomorrow morning, please let us know as soon as possible. Then we can prepare more in depth into that direction. Yeah.
Philip, you got the votes of the applications for tomorrow?
Yes. So, first of all, thanks.
Was willst du?
Das HDMI-Kabel leih ich mir dann nochmal kurz aus, ja. Or are there some last-minute votes?
I'm opening it, but it doesn't.
Ah yeah, you have to know the secret. Schauen wir mal.
I want to do something.
So, have
the numbers changed. Yeah, so we have had already a look on it before, a little bit in detail. So, I think now the numbers have changed. Oh my goodness. Okay, so I think we will do the first session. Yeah, let me first go to the program. So, as already mentioned, we have now this 1 hour session in the morning, and then das ist klar. And then we have the coffee break. So we have moved the coffee break for half an hour, and then we have this last block with an open end and open discussions as long as you want. So I think we will do 2 sessions in parallel. I guess the NGSolve and the NGStreffs, which has a very broad somehow spectrum. So we will do some fluids and Treffs, Paul. Yes, I don't know where you are. Okay. Yeah, and if then there are some more details, interests, probably we will do this in smaller sessions, I guess. Okay, so it is now 5:15, more or less. We have the workshop dinner, where is it? At the Abaddon Bistro, which is here. So here is the Gästehaus. You already know the Blattwerk Mensa, so the Blatt Mensa. And when you continue walking here, here at the corner there is the bistro. And we have the workshop dinner starting at 19 in the evening, so 7 o'clock in the evening, 7 p.m. You can stay up until then here, so I think we will start walking from here probably, yeah, I don't know, 6:30 or 20 to 7, yes. And you can join with us. Okay, anything else, Joachim? Nope. All right, then see you later.